You wake up in a world that seems perfectly logical. Apples fall from trees. Shadows move with the sun. Planets trace curves across the sky. It all feels smooth, dependable, like a giant, invisible clockwork ticking in the background. Everything has a cause. Everything makes sense. It's comforting, almost poetic. The universe as a machine, following rules we can discover. For centuries, this is how physicists saw reality. And then it broke. Not all at once, but in tiny, shattering moments. A strange experiment here. A suspicious result there. Cracks appeared in the machinery. And when scientists tried to patch them, they found something terrifying underneath. The universe doesn't play by our rules. Let's go back to the early 1900s. Physics had become confident. Maybe too confident. Isaac Newton had explained motion, gravity, and the planets. James Clerk Maxwell had described light as an electromagnetic wave. The laws seemed universal, final, complete. But then came the cracks. First, Max Planck noticed something odd about how objects glow when heated. Classical physics said the energy should climb to infinity, which it obviously doesn't. So he made a strange assumption, maybe energy comes in little chunks. He called them quanta. It was just a mathematical trick, a patch, but it worked. A few years later, Albert Einstein, yes, that Einstein, took the idea further. He suggested that light itself might come in packets. Not just a wave, but a particle, a photon. Suddenly, light wasn't what we thought it was. It was both particle and wave, depending on how you looked. Then Niels Bohr proposed a model of the atom where electrons could only exist in specific orbits, jumping between them in sudden, unexplained leaps. This was not normal science. These were not gentle refinements. These were earthquakes. Every new experiment seemed to contradict what came before. Electrons didn't follow paths. They blurred. Light went through two slits at once. Observing a system seemed to change the system. The more physicists tried to pin things down, the more reality slipped through their fingers. By the 1920s, it was clear. The universe wasn't just strange. It was quantum. And quantum mechanics didn't describe particles moving along definite paths. It described probabilities, waves of possibility that collapsed into certainty only when observed. Until then, a particle wasn't here or there. It was both. It wasn't spinning up or down. It was everything, all at once, until forced to decide. This wasn't just uncomfortable. It was offensive to many of the great minds of the time. Einstein, for one, refused to believe it. God does not play dice, he said. He wasn't objecting to the math. The math worked. What he rejected was the idea that the universe was fundamentally random, that nature made choices based on chance, that reality itself was, at its core, unknowable. But the experiments kept coming, and the results couldn't be denied. By the time Werner Heisenberg proposed his famous uncertainty principle, that you couldn't simultaneously know a particle's position and momentum, physics had crossed a threshold. There was no going back. Classical physics, the universe as machine, was over. The new world was blurry, uncertain, wildly successful, and deeply unsettling. And then came something even stranger. An idea so weird, even the founders of quantum theory weren't sure what to make of it. They called it entanglement. It suggested that two particles, once linked, could stay connected no matter how far apart they were. That measuring one would instantly affect the other, even across galaxies. To Einstein, it was madness. Spooky action at a distance. He called it, and he meant it as an insult. But others weren't so sure, because if it was true, it meant that space itself didn't matter. That connection was more fundamental than distance. That the very structure of reality was stitched together in a way we had never imagined. That's the mystery at the heart of this story. Over the next chapters, we'll follow it. From philosophical debates to real-world experiments, from Einstein's protests to satellites orbiting Earth, from black holes to the edge of meaning itself. Because entanglement isn't just a scientific curiosity. It's a portal into a deeper understanding of the universe, and maybe of ourselves. Welcome to this journey. You're watching The Midnight Particle. Einstein versus the New Physics. Albert Einstein was no stranger to revolution. He had upended physics once already. In 1905, when he showed that time could stretch, mass could convert into energy, and light could push objects like wind in a sail. His theory of relativity made him a legend, the kind of scientist whose ideas could bend the universe around them. But when the quantum revolution began to take shape, Einstein, the revolutionary, became the skeptic. He didn't dismiss quantum mechanics out of ignorance. On the contrary, he helped invent it. It was his paper on the photoelectric effect that first proposed light might come in packets. That work won him the Nobel Prize. But the more quantum mechanics developed, the more it twisted into something Einstein couldn't accept. It wasn't just weird, it was wrong, at least in his view, because it broke something sacred to him. The belief that the universe is governed by laws that are real, complete, and independent of us. Quantum theory, by contrast, said that particles didn't have definite properties until they were observed. That reality came into focus only when measured, that the world, at its most fundamental level, was built on probability, not certainty. To Einstein, that wasn't science. That was surrender. He wanted a world you could explain, not one you had to guess your way through. The growing quantum movement, led by brilliant minds like Bohr, Heisenberg, Schrödinger, Dirac, embraced the mystery. They weren't troubled by the uncertainty. They celebrated it. They saw quantum mechanics as a strange but beautiful framework, one that matched experiment after experiment with astonishing precision. But Einstein remained unconvinced. At first, he tried to fix the theory, to imagine a deeper layer beneath the uncertainty, a hidden set of rules that made everything make sense again. He called it a hidden variable theory, an idea that perhaps particles did have properties before you measured them. We just didn't know how to look. It was like shuffling a deck of cards. You don't know what card is on top, but that doesn't mean it doesn't have a value. You're just missing information. That's all. But quantum mechanics didn't allow for that. It didn't say, we don't know. It said, there's nothing to know yet. Until you check, the particle exists in multiple states at once. It's like every card in the deck is both red and black, every number at once, until you flip it over. Einstein couldn't accept that. And so, in the 1920s and 30s, he began a quiet war. Not with rage, not with mockery, but with thought experiments. Scenarios designed to test the internal logic of quantum theory, to expose its cracks. One of his most famous involved a box filled with light and a delicate clock. It was a trap, meant to catch the uncertainty principle in a contradiction. Bohr, Einstein's old friend and fiercest opponent in this battle, responded by using Einstein's own theory of gravity against him, a poetic reversal that only deepened the divide. These weren't casual debates. These were battles of worldviews. Einstein believed in a universe that existed whether we were watching or not, where reality was out there, objective, consistent, waiting to be discovered. Bohr believed in a universe where the act of observing wasn't passive, it was creative, where the observer and the observed were intertwined, where the question you asked changed the answer you got. Both men were geniuses. Both men were sincere, but they couldn't agree on what the universe was. And beneath all the equations and arguments, one idea kept haunting the conversation: entanglement. It was a prediction of quantum mechanics that Einstein found especially horrifying, because it suggested that particles could remain linked across any distance, influencing each other instantly. If true, it would mean the universe was connected in a way no classical theory could explain. Einstein called it spooky action at a distance, not as a joke, but as a warning. He believed this was the final proof that something was missing. That quantum mechanics couldn't be the whole story. That behind the curtain of probability, there had to be a deeper mechanism, some hidden truth still waiting to be uncovered. He wasn't alone in thinking this. Many physicists hoped he was right. That quantum theory, brilliant as it was, would one day be replaced by something better, something more intuitive, more complete. But as the years passed, no such theory emerged. And so, in 1935, Einstein decided to go public with a paper that would lay out his challenge once and for all. A paper that would force the world to confront the most disturbing question in physics. Is this theory, this strange, slippery, impossibly accurate theory, actually describing reality? And if not, then what is? What does entanglement mean? It began as a mathematical curiosity. Entanglement. A strange prediction buried inside the equations of quantum mechanics. No one quite knew what to make of it, not even the people who discovered it. And yet, over time, it became the heart of the mystery. The part that made Einstein furious. The part that made Bohr pause. The part that made everyone else wonder whether we'd misunderstood the very fabric of reality. So what does it actually mean? Let's start simple. Imagine two playing cards. Say, one red, one black. You put them into two envelopes, shuffle them, and mail them to opposite ends of the earth. When someone opens their envelope and sees the red card, they instantly know the other one is black. No big deal. That's classical correlation. The cards had definite colors the whole time. You just didn't know which was which. Learning the state of one reveals the state of the other. But nothing spooky is going on. There's no signal, no magic, just shared information, separated by distance. But now imagine something different. Two quantum particles are created in a special way, a process that links them not by color or position, but by something deeper, their quantum states. Maybe it's their spin, maybe it's polarization. It doesn't matter. The key is this. When one particle is measured, the other instantly knows, even if it's on the other side of the universe. And more importantly, neither particle had a definite state to begin with. Unlike the playing cards, they weren't secretly red and black all along. They were in a superposition, a blurred cloud of possibilities until the moment of measurement. And then, click. One particle snaps into a specific state, and the other, no matter how far away, snaps too, instantly. It doesn't matter if they're in the same room or a billion light years apart. When one is measured, the other behaves as if it was part of the same system. Because it was. This is entanglement. A connection so deep, so perfect, so beyond anything in classical physics that even Einstein didn't believe it could be real. He thought there had to be some hidden mechanism, some unseen code that each particle carried with it from the start. That they weren't reacting to each other, but just revealing something they already had. But the mathematics of quantum theory said no. It said the particles weren't just connected, they were inseparable. Not in a physical sense, but in an informational one. Their individual identities didn't exist until observed. Their fates were tied, not because of wires or signals, but because of how they were created. They were entangled. Here's an analogy. Think of a coin spinning in midair. It's neither heads nor tails. Not until it lands. Now imagine two coins spinning in two different places, and somehow, every time you catch one and it's heads, the other lands tails. Every single time, no matter how far apart they are. No communication, no trick. That's not correlation. That's quantum. And it gets even weirder. You can entangle more than just two particles. You can entangle millions. You can entangle particles across space, across time. You can entangle them in ways that don't even make intuitive sense, where their connections only show up when you look from a certain angle or ask a certain question. And the implications? They're staggering. Because if this is how nature works, if things that look separate are actually parts of the same system, then distance is an illusion. Then locality. The idea that things can only affect each other through nearby interactions isn't always true. That was the part Einstein couldn't accept. To him, nothing should happen faster than light. No influence should reach across the cosmos in zero time. But entanglement doesn't care. It's not about speed, it's about structure. About a kind of togetherness that space and time can't touch. It's easy to misunderstand. People hear about entanglement and think it means you can send messages faster than light. But you can't. The results are random. There's no signal to send. What you get instead is something subtler, deeper. Correlations that can't be explained by any classical means. Correlations that shouldn't exist, and yet do. You can't use them to send information, but you can use them to ask a question. Is the universe really made of separate parts? Or is it something more like a whole, with entanglement as the invisible thread holding it together? That question stayed unanswered for decades. But Einstein wasn't done. In 1935, he took entanglement, this eerie, unsettling idea, and built his most powerful attack against quantum theory. A final challenge, a paper that would declare, calmly and surgically, that something about this strange new physics was incomplete, and that if quantum mechanics really allowed this spooky behavior, then the theory itself must be wrong. The EPR paper, A Challenge to Reality. In 1935, Einstein made his move. Together with two younger collaborators, Boris Podolsky and Nathan Rosen, he published a paper in the Physical Review titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" It wasn't a flashy title. It didn't need to be. Because behind that calm question was a bold accusation: quantum mechanics doesn't describe reality. Not fully, not truthfully, not completely. This was the infamous EPR paper, named after its authors. And its goal was simple: to expose the limits of quantum theory, to show, once and for all, that this strange new physics couldn't be the final word. Einstein didn't attack the math. The math was flawless. Instead, he attacked what the math meant. The heart of the paper was a thought experiment. It went something like this. Imagine you have a pair of particles, let's say electrons, that are created together in a special state. They shoot off in opposite directions. According to quantum mechanics, these particles are entangled. They don't have individual properties. Not yet. Their momenta, positions, spins. They exist only in relation to each other. Now here's where it gets interesting. You measure the position of particle A. Instantly, you know the position of particle B, even though you never touched it. Or, instead, you choose to measure the momentum of particle A. Same thing, you instantly know the momentum of particle B. But here's the catch. Position and momentum are what quantum physicists call complementary variables. You can't know both at once. The more you know of one, the less you can know of the other. It's Heisenberg's uncertainty principle, a core tenet of quantum theory. Yet, in this setup, by choosing what to measure on A, you seem to be deciding what's true for B. And not just deciding instantly, across any distance. Einstein, Podolsky, and Rosen argued that this was absurd. If measuring A gives you certain knowledge about B, then B must have had that property all along. It must have been real, not just a probability cloud, not a mathematical ghost. A real, definite thing, even before you measured anything. And if that's true, then quantum mechanics, which says B didn't have a value until the measurement, must be incomplete. That was the conclusion of the paper. Not that quantum mechanics was wrong, but that it was missing something. Some deeper layer of reality. Some hidden variables that the theory didn't account for. The EPR paper was sharp, technical, and surgical. It didn't rant. It didn't speculate. It just followed the logic, calmly, relentlessly, to a place quantum theorists didn't want to go. Einstein thought it was checkmate. But then came Bohr. And Bohr's reply wasn't what anyone expected. He didn't try to explain how the distant particle knew what the other was doing. He didn't deny the weirdness. He didn't even reject the conclusions directly. Instead, he did something stranger. He challenged the question itself. Bohr said, "You're making an assumption that particles have definite properties before they're measured. But what if that assumption is just wrong? What if reality doesn't exist in a definite state until it's observed? What if position, momentum, spin, all the things we think particles have, are not properties of the particle alone, but of the whole experiment? In other words, you can't talk about what's real for particle B without considering what measurement was made on particle A." It was a radical idea. To Bohr, the entire framework of the EPR paper was built on classical assumptions that no longer applied. He believed quantum mechanics wasn't incomplete. It was redefining what it meant to be complete. But the physics community was divided. Some thought Bohr was right, that Einstein was clinging to an outdated picture of reality. Others thought Bohr was dodging the question, using philosophical fog to cover a hole in the theory. And for years, the debate stayed there, unresolved. Because even if Einstein was right, even if there were hidden variables, there seemed to be no way to prove it. The predictions of quantum mechanics matched every experiment. There was nothing to test, nothing to observe. It was like arguing about what's behind a locked door, with no key, until someone found one. Someone who read the EPR paper and asked a very different question. What if there's a way to tell the difference? What if this isn't just philosophy anymore? Bohr strikes back, philosophy, arguments, and strange replies. Bohr read the EPR paper with the intensity of a man being personally challenged. Because in a way, he was. It wasn't just a disagreement over math. It was a confrontation between two worldviews. Einstein had drawn the line. He had declared that quantum mechanics, for all its success, was incomplete. That something real and hidden still lay beneath the surface. Bohr disagreed, but not in the way most people expected. He didn't respond with a clean counterexample or a neat mathematical proof. Instead, Bohr did something far more frustrating and far more profound. He questioned the question itself. To Bohr, Einstein's mistake wasn't in the logic. It was in the assumptions beneath the logic. Assumptions that seemed obvious, but weren't. Like this one, that physical properties exist independently of how we measure them. Bohr didn't think that was true anymore. He believed that the act of measurement wasn't just a way to reveal what's there. It was a part of the system. You can't describe the outcome of an experiment without describing the entire context. What was measured, how it was measured, when, and with what. In the classical world, this sounds like nonsense. If you measure the length of a stick, you assume the stick had that length whether you measured it or not. Reality is objective. It doesn't depend on what tools you use. But in the quantum world, Bohr said, not so fast. He argued that when it comes to particles like electrons or photons, the measurement doesn't just reveal reality, it defines it. Before measurement, a quantum system doesn't have fixed properties. It has possibilities. It's in a superposition, a blend of outcomes weighted by probability. Only when you interact with it in a specific way do those probabilities collapse into a concrete result. So when Einstein asked, how does particle B know what measurement was made on particle A, Bohr's answer was something like, you're not allowed to ask that, because those properties didn't exist until the measurements were made. You're trying to assign values to things that weren't real? It was infuriating to Einstein. He had spent his life building theories that described a world that existed whether or not anyone was looking. To him, Bohr's view was dangerously close to mysticism, a surrender of science's duty to describe an objective, observer-independent universe. But Bohr didn't flinch. At the famous Solvay conferences in the late 1920s and early 1930s, Einstein kept proposing thought experiments, clever setups meant to expose contradictions in quantum mechanics. Bohr responded to each one with a kind of calm, cryptic precision. In one case, Einstein suggested using a box of light and a weighing scale to measure energy and time simultaneously, something quantum mechanics said couldn't be done. Bohr's rebuttal? He used Einstein's own theory of general relativity to show that the measurement would disturb the system and preserve the uncertainty principle. It was the ultimate counterpunch. But the truth is, they were arguing past each other. Einstein wanted an answer to a specific question. Do particles have properties before we measure them? Bohr was saying that question makes no sense in the quantum world. And so, the two greatest physicists of their generation reached a kind of stalemate. Einstein thought Bohr was dodging the real issue. Bohr thought Einstein was trapped in outdated thinking. And the rest of the physics community? They chose pragmatism. Quantum mechanics worked. It explained everything from the structure of atoms to the color of stars. You could use it to build lasers, transistors, even the very foundations of modern computing. So most physicists shrugged off the philosophical weirdness and moved on. But the discomfort never really went away, because buried inside Bohr's reply was a disturbing implication, that reality itself is not fully real until someone looks. It's not just that particles don't have definite properties, it's that reality doesn't decide what's true until it's forced to. And entanglement, this spooky, unsettling link between distant particles, wasn't a bug. It was a feature, a consequence of a world where measurement and reality are hopelessly tangled. But if that's true, how far does it go? Can you really build an entire theory on a foundation where things aren't real until observed? What happens when you try to make predictions? Can a universe like that even be tested? For decades, it seemed like no one could answer those questions. And then one man did, not with philosophy, not with words, but with a trick, a mathematical trap, a way to force the universe to reveal whether it was truly quantum or hiding something deeper all along. John Bell's brilliant trick. By the 1960s, the debate seemed dead. Einstein had passed away. Bohr too. The quantum pioneers had moved on, and a new generation of physicists didn't have time for philosophical puzzles. Quantum mechanics worked. It powered chemistry, electronics, nuclear physics. Why argue over whether particles really exist when you could build something with them? But in the quiet offices of CERN, the European Particle Physics Lab, there was one man who couldn't let the question go. His name was John Bell. Bell wasn't a philosopher. He wasn't even a quantum theorist by training. He was an engineer, a practical physicist. But he had a deep curiosity and a mind like a scalpel. And in 1964, Bell did something extraordinary. He read the EPR paper, Einstein's final, elegant critique of quantum theory. He read Bohr's reply, cryptic and philosophical, and then he asked a question neither of them had thought to ask. What would a universe look like if Einstein was right? That is, if there were hidden variables, if particles really did have properties before they were measured, what exactly would the statistics of their measurements look like? Not in vague terms, not just philosophically, mathematically. He built a model, a simple one. Two particles created together and shot apart. Each one arrives at a detector, one with Alice, one with Bob. At each detector, there's a switch. You can choose to measure the particle's spin at one angle or another. Now here's the key idea. If the particles are just carrying instructions like little scripts that say, if the detector is set to this angle, give this result, then there are limits to how well their answers can match across many trials. It doesn't matter how clever the hidden variables are. No local, pre-programmed strategy can beat the math. Bell wrote the equation, a boundary, a limit on how strong the correlations could be. That boundary became known as Bell's inequality. And then he checked what quantum mechanics predicted, and it violated the boundary, flat out. Quantum theory said that under certain measurement settings, the results from Alice and Bob would be more strongly correlated than any local hidden variable theory would allow. This was not just weird, it was revolutionary. Because now, for the first time, there was a testable difference between Einstein's world and Bohr's. If you run the experiment and the correlations obey Bell's inequality, then Einstein was right. The world is local, real, deterministic. But if the inequality is violated, then something has to give. Either particles don't have definite properties until measured, or distant events can affect each other instantly, faster than light, or maybe both. Bell had done the impossible. He had taken a philosophical argument, long dismissed as untestable, and turned it into an experiment. Not a thought experiment, a real one. It meant that this wasn't just about ideas anymore, this was about data. Of course, there was a catch. Actually performing the experiment was incredibly difficult. You needed a source of entangled particles. You needed fast, reliable detectors. You needed to make random choices at the last possible moment to avoid any hidden communication. In the 1960s, that wasn't realistic. But Bell planted the seed. His paper sat quietly in the literature for years, largely unnoticed. But slowly, it began to circulate. A few physicists read it. A few more became obsessed. And then, in the 1970s, someone finally tried. Not with fancy equipment, not in a billion-dollar lab, just with a little funding, a lot of patience, and the conviction that this question still mattered. They would take Bell's inequality into the real world. And physics would never be the same. The first tests of entanglement. It began, like many breakthroughs do, in a lab that no one was paying much attention to. In the early 1970s, Bell's theorem was still obscure. Most physicists considered it philosophical, clever, but irrelevant. Quantum mechanics was too successful to worry about. There were atoms to smash, semiconductors to design, nuclear models to refine. Who had time for spooky action at a distance? But a few people couldn't let it go. One of them was an experimental physicist named John Clauser. He was young, persistent, and crucially, willing to look weird. In 1972, with his colleague Stuart Friedman, he built the first serious test of Bell's inequality. It was a delicate setup. They used calcium atoms, excited in just the right way so that when they decayed, they emitted two entangled photons, particles of light, heading in opposite directions. One toward detector A, one toward detector B. At each detector, they could choose what polarization angle to measure, just like Bell imagined, a kind of quantum coin toss. And just like in Bell's scenario, the key was to compare the results to see how strongly the two measurements correlated. If Einstein's picture was correct, if each photon carried hidden instructions about how to respond, the correlation should stay within Bell's inequality. But they didn't. They violated it. Not by much, not dramatically, but enough. Clauser and Friedman had seen something the world wasn't quite ready for, evidence that quantum entanglement was real, and that the universe might not be local after all. Still, the experiment had limitations. The detectors weren't very efficient. The measurement settings weren't changed fast enough to completely rule out communication between the detectors. There were loopholes, little cracks in the design that gave skeptics a way out, and many took it. Some physicists questioned the assumptions. Others said the results could be explained by experimental error. Still others admitted it was interesting, but not convincing. Not yet. But the door had opened. Through the 1970s, more experiments followed. Researchers in Germany, the US, and the Soviet Union began to replicate and improve the setup. Each test brought a little more precision, a little more clarity, and each time Bell's inequality was violated again. What was happening wasn't just confirmation of quantum theory, it was something more unsettling. These weren't tests of equations, they were tests of reality. They were asking, do particles have properties before we look? Is space a barrier, or just an illusion? Can the universe be explained by local causes? Or are we seeing something truly non-local, where events in one place depend on choices made in another, instantly? But no experiment is perfect. Skeptics pointed to the detection loophole, the idea that the detectors only registered a small percentage of particles, and maybe those were the ones that just happened to fit the theory. Or the locality loophole. Maybe the detectors weren't far enough apart, or weren't switched quickly enough, and some hidden signal still slipped through. The physics community was intrigued, but still cautious. These results were provocative, but not yet bulletproof. And then, in the early 1980s, someone came along who would change that. A French physicist with a gift for precision and an obsession with loopholes, Alain Aspect. He saw the weakness in every test that had come before and decided to fix them all. What he did next would finally force the world to take entanglement seriously. Alain Aspect's breakthrough, closing loopholes, shocking results. In 1981, a quiet revolution began in an optics lab just outside Paris. The physicist leading it was Alain Aspect, precise, methodical, and unusually stubborn. He didn't set out to become a philosopher. He didn't even consider himself controversial. He just wanted to know, with absolute certainty, whether the world behaved the way quantum mechanics claimed it did, because until that point, no one had done it cleanly. Yes, experiments had violated Bell's inequality, but every one of them left room for doubt. Tiny gaps, technical imperfections, the infamous loopholes. Aspect wanted to close them, all of them. So he did something no one else had dared to try. He rebuilt the experiment from the ground up, with better detectors, faster electronics, and a more elegant photon source. He used calcium atoms to produce pairs of entangled photons, just like Clauser had done. But his setup was different in one crucial way. He randomized the measurement settings during flight. That sounds simple, but it's revolutionary. Because now, instead of choosing the detector settings in advance, his system made the choice while the photons were already on their way. The measurement basis was flipped, randomly, quickly, independently, in the tiny window of time it took for light to cross the lab. This was a direct assault on the locality loophole. No hidden variable could possibly know what setting the detector would choose. There wasn't enough time for information to travel, not even at the speed of light. It was the cleanest version of Bell's test the world had ever seen. And when he ran it, the results were clear. Bell's inequality was violated, again, stronger than before, more convincingly, with more precision. The predictions of quantum mechanics held. The idea that particles had predetermined properties, rejected. The idea that space was a barrier, shattered. The measurements at one detector correlated with the measurements at the other, even though the settings were changed at the last moment, and no signal could pass between them. Einstein's dream of a local, hidden variable reality was collapsing, not in theory, but in real time, under real lights, in a real laboratory, and the world began to notice. Aspect's results were published in 1982. They sent a ripple through the physics community. No longer could entanglement be dismissed as a philosophical curiosity. It was experimental fact, something we could measure, predict, and confirm. Still, the skeptics pushed back. They pointed to the detection loophole, still unresolved. What if the detectors only captured a biased sample of particles? What if the strange results were just a statistical illusion? Aspect knew this. He never claimed to end the debate. But he had brought it to a place where it could no longer be ignored. And perhaps even more importantly, he had shown the world that testing the foundations of reality was possible, that the deepest questions of physics were not off limits, that we didn't have to choose between success and understanding. We could have both. After Aspect, the race was on. New labs around the world began building ever more precise versions of his experiment, closing loopholes one by one. Faster switches, better detectors, larger distances, satellite links, cosmic photons used as random number generators. Each step brought us closer to the unavoidable truth. Entanglement is not a trick. It's not a gap in knowledge. It's not a sign of incompleteness. It's how the universe works. And yet, one final question remained. If particles influence each other instantly across space, if the results are connected in ways no classical system can explain, then what exactly does that say about the nature of space itself? Local versus non-local reality. What does instantaneous really mean? The results were in. Bell's inequality had been violated again and again. Photons entangled in labs across the world kept behaving in ways no classical theory could explain. No hidden variables, no invisible signals, just a strange, persistent connection. But now came the harder question. The deeper question, what does instantaneous really mean? When two entangled particles are measured far apart and their results show correlations beyond classical limits, it feels like one particle is affecting the other immediately, across space, with zero delay. That's what Einstein found so disturbing. He called it spooky action at a distance. And from a classical perspective, he was right to be suspicious. Because in relativity, nothing can travel faster than light. No cause can jump from one point in space to another without time passing. The speed of light isn't just a limit, it's the structure of space-time itself. So how could this work? How could a measurement here influence the outcome there instantly? Let's break it down. In every experiment, the two entangled particles are created together, born from the same process, sharing the same quantum state. They fly apart, sometimes for kilometers. Then they're measured, but the choice of what to measure, the angle of polarization, the direction of spin, is made after they've separated. And when you compare the outcomes, they're correlated. Not in a simple both yes or both no way, but in a pattern that violates Bell's inequality. A pattern that cannot be explained by any local instruction the particles might have carried with them from the beginning. It's as if the universe, in that moment of measurement, is non-local, not divided neatly by space, but woven together by something deeper. But here's the twist. Even though the measurement outcomes are correlated, they're still random. If Alice gets spin up, she can't use that to send a message to Bob. She doesn't control the result. She only knows that Bob's result will match hers in a certain way after the fact. So no usable information travels faster than light. No message. No signal. Just reality, snapping into shape across space like two halves of a single thought. And that's the puzzle. From the outside, it looks like one particle is instantly affecting the other. But from within the quantum framework, nothing is being sent. The entangled pair is described by a single mathematical object, a joint state. It doesn't make sense to talk about what particle A is doing independently from B. They're not two separate systems anymore. They're part of one extended system, a quantum whole that spans space. This is the idea of non-locality. Not action at a distance in the way Newton imagined, forces reaching out across emptiness, but a kind of built-in togetherness. A global structure that doesn't care about distance. And it's not just a metaphor. Non-locality is quantifiable. It's measured. It's in the data. It's real. But does it mean space isn't real? Does it mean our idea of cause and effect is broken? That's still up for debate. Some physicists try to interpret the data with hidden variables that are non-local, meaning, yes, the particles do influence each other instantly, but in a way that's consistent with the math. Others prefer interpretations where nothing travels because there's no thing to travel, just a web of probabilities that collapses into outcomes when observed. Still others explore exotic ideas, multiple worlds, retrocausality, even space itself emerging from entanglement. The experiments don't tell us which picture is true. They just tell us what cannot be true, that particles have their own separate fates, that measurements are independent events, that the world is, at its root, local and classical. Because it's not. It's quantum. And quantum means entangled. It means the world is stitched together in ways we're only beginning to understand. And the deeper we look, the more unsettling it becomes. Because even now, some physicists are still trying to find ways to explain it without giving up locality. Without letting go of the old rules, but the evidence keeps coming. And soon, one by one, every loophole will be gone. The loopholes fight back. Critics, counterarguments, and stubborn physicists. Physics has always had skeptics, and in the case of quantum entanglement, the skeptics had a point, because even as experiment after experiment violated Bell's inequality, there was always a little room to wiggle, always a loophole, a small crack in the design that kept the door open for doubt. And doubt, in science, is healthy. The stakes were enormous. These weren't just technical disagreements. These were claims about the nature of reality, about whether the universe obeys local causality, about whether objects have properties before you look. So the skeptics fought back, not out of denial, but out of rigor. They didn't deny the data, they questioned the setup. And their questions centered around three major loopholes. First, the detection loophole. No detector is perfect. In early experiments, the machines that captured particles, usually photons, only registered a small fraction of them. Most of the entangled particles simply vanished, unmeasured. So the critics asked, what if the particles that actually got detected were just a biased sample? What if the universe did obey local realism, but only the rare cases that looked quantum happened to get picked up? It's like running a survey, but only asking people who already agree with you. Maybe the detectors were selecting the results that fit Bell's violation and ignoring the rest. Second, the locality loophole. Even in Alain Aspect's clever experiments, where detector settings were switched mid-flight, skeptics argued there might still be time, in principle, for a signal to sneak between detectors. Maybe the timing wasn't perfect. Maybe some hidden information traveled just fast enough to influence both measurements. Sure, it would have to be faster than light. But if you believe in hidden variables, maybe that's just what they do. After all, no one's seen them. Why assume they obey ordinary rules? Third, the freedom of choice loophole. This one was more subtle. In Bell's experiment, you assume that the choice of what to measure, spin up or down, polarization at this angle or that, is free. That the detector settings are not somehow influenced by the same hidden variables that define the particle outcomes. But what if that assumption is wrong? What if the settings themselves are not truly random? What if the entire experiment, particle creation, detector settings, measurement results, is woven together in some invisible, conspiratorial way? In other words, what if the universe is super-deterministic? A mouthful, but the idea is simple. Everything is connected in advance. There is no true randomness, not even in our choices. It just looks random because we don't see the full picture. To many physicists, this felt like giving up, like throwing out free will and scientific testing itself. If you assume everything is rigged from the start, what's left to test? But still, the loophole stood. And that was the problem. Quantum theory was passing every test, but no test was airtight. Each had some possible backdoor for local realism to escape through, so physicists got to work. Over the next few decades, they designed experiments specifically to close these loopholes, one by one. They built better detectors, more efficient, more accurate. They used electrons, atoms, ions, particles easier to catch than photons. They placed the detectors far apart, kilometers, sometimes even farther. They used fast random number generators, including cosmic sources, like starlight or radiation, to guarantee that the measurement choices weren't pre-programmed. It was like building a scientific mousetrap, patching every exit, blocking every path that hidden variables could take. It was slow. It was technical. It wasn't flashy. But it was decisive. Because if you could run just one experiment that closed all the loopholes at once, no detection bias, no communication, no conspiracy, then the argument would be over. And by the early 2010s, that moment had nearly arrived. A final set of tests. Multiple labs, multiple countries, independent teams, all preparing to slam the door shut on local realism. The final verdict: 21st century experiments that sealed the case. By the time the 21st century arrived, the battle lines had been redrawn. This was no longer a war of words between Einstein and Bohr. It was no longer a question reserved for textbooks and thought experiments. This was now a problem for engineers. How do you build a machine that can test the limits of reality itself? The goal was clear: perform an experiment that closed every single loophole. No assumptions, no exceptions, no excuses. Just a pure, final, unambiguous test of Bell's inequality. And in 2015, after decades of theoretical buildup, experimental refinements, and technical breakthroughs, it finally happened. Actually, it happened 3 times, in 3 different labs, one in Delft, Netherlands, one in Vienna, Austria, one in Boulder, Colorado. Independent, simultaneous, coordinated only by curiosity and competition. Let's start with Delft. Physicists there used entangled electrons, trapped in tiny pieces of diamond. These particles were easier to isolate and measure than photons, and they stayed entangled long enough to separate the measurements by over a kilometer. Then they used fast, random number generators to choose the detector settings after the particles were already flying. The choice was made in microseconds, so fast that no signal, not even at the speed of light, could pass between the detectors in time. And then they ran the numbers. Bell's inequality was violated, with all known loopholes closed. Detection? No issue. Locality? Airtight. Freedom of choice? Randomized in real time. Next was Vienna. This team used entangled photons, fired between 2 buildings across the city. But this time, they went further. The random number generators were built using cosmic radiation, ancient starlight, billions of years old, selected in real time to set the detector angles. Why? To guarantee that no hidden variable could have secretly influenced both the particles and the measurement choices. If the settings were based on starlight from different galaxies, then the conspiracy would have had to begin before Earth even formed. And still, Bell's inequality was violated again. Same in Boulder. Different particles, different equipment, same result. Over and over, nature gave the same answer. Entanglement is real. Local realism is dead. If you want to explain the results using hidden variables, you have to break one of 2 pillars: locality, the idea that nothing can influence anything else faster than light; realism, the belief that particles have properties before we measure them. You can't keep both. And most physicists, faced with that choice, accept the unthinkable: that either space doesn't fully separate objects, or that reality doesn't exist until we ask about it. There's no more wiggle room. No more, maybe the detectors were biased. No more, maybe the particles were coordinating behind the scenes. No more, maybe we just don't understand the math. We understand the math. We've done the experiments, and the universe is not classical. That doesn't mean we understand it fully. Far from it, but it means the old picture. The neat little machine ticking away in the background, with particles as tiny billiard balls, is gone, replaced by something stranger and more beautiful. A universe built not from separate things, but from relations. Not from positions and velocities, but from probabilities and correlations. Not from local cause and effect, but from entanglement. And yet, even now, after a century of theory and a half-century of experiments, there's one question physicists still whisper, usually late at night, when no one's listening. If 2 particles can affect each other instantly across space, then what is space, really? Quantum teleportation, how information jumps without traveling. For decades, entanglement was an enigma. It haunted philosophers, confounded physicists, and stubbornly refused to behave like anything classical. But, eventually, after all the arguing, all the measuring, all the loopholes closed, a new question emerged. If this is how nature works, can we use it? Can we harness entanglement? Not just observe it, but build with it? The answer, shockingly, is yes. And it starts with something that sounds completely impossible: quantum teleportation. Let's be clear. This isn't science fiction. We're not beaming people across space. No atoms are disassembled or reassembled. No transporters. No shimmering light effects. But something stranger is happening. Because quantum teleportation is about moving information, not matter, in a way that classical physics says should be impossible. So how does it work? Start with a quantum state, a single particle, like a photon or an electron, in an unknown configuration. It could be spinning up, it could be spinning down, or it could be in a weird superposition, both at once, weighted by probabilities only nature knows. This quantum state is fragile. The moment you measure it, you destroy it. You can't copy it either. That's a law of quantum mechanics, the no-cloning theorem. Once you try to duplicate a quantum state, it's gone. You get one shot. So, how do you move it? Here's the trick. You need 3 particles. Let's call them A, B, and C. A is the particle holding the quantum state you want to send. B and C are entangled, created together, like our old friends from Bell's experiments. B stays with you. C is far away, maybe with a colleague on the other side of the lab or the other side of the world. Now you take particle A and entangle it with particle B. You perform a special kind of measurement that links their states, called a Bell state measurement. What happens next is bizarre. That measurement destroys the original quantum state in A, but it also transfers the information into particle C. Instantly. Not by copying it, not by sending it, by reconstructing it. It's as if the quantum state of A disappears from one place and reappears in another, without ever existing in between. But wait, there's a catch. To complete the teleportation, you still need to send your measurement result, just 2 classical bits of information, to the recipient. That tells them how to apply the correct transformation to C, so it matches the original state of A exactly. In other words, the quantum part, the structure of the state, is transferred via entanglement. The classical part, the final step, still travels at normal speed. No faster-than-light messaging. No violation of causality. And yet, the quantum information has moved, without crossing space. When this was first proposed in the early 1990s, it sounded like fantasy, but in 1997 it became reality. Physicists in Austria performed the first successful quantum teleportation of a photon's polarization state. It worked. Since then, teleportation has been demonstrated with atoms, ions, electrons, and photons, across fiber optic cables, through the air, and even from the ground to orbit. And each time, it confirms something wild. You can move quantum information without moving the thing that carries it. This has massive implications, because in the classical world, information always rides on something: electrical pulses, radio waves, physical letters. You can't separate the message from the medium. But in the quantum world, the message is the medium. And with entanglement, we're learning how to untangle space itself. Now, if this sounds like a neat trick with no real-world use, think again. Quantum teleportation is the foundation of the quantum internet, a next-generation network where data isn't just encrypted, it's entangled. It's also a core part of quantum computing, quantum communication, and even quantum metrology, the science of ultra-precise measurements. But above all, quantum teleportation proves something profound: that entanglement isn't just a ghostly curiosity from the edges of physics. It's a resource, a tool, a thing we can shape and use, not to defy physics, but to explore it more deeply. In a way, teleportation is the first time we stop staring at entanglement from the outside and start stepping inside. Because once you realize that quantum states can be transferred without motion, that information can jump across the void without ever being sent. You begin to ask, what else can we do with this? What would a global web of entanglement look like? How far can we stretch this thread before it snaps? And what happens when you connect not just 2 particles, but millions? We're no longer talking about strange thought experiments in isolated labs. We're talking about a new kind of network, one built not from wires or waves, but from entanglement itself. The quantum internet building networks with entangled photons. If the classical internet is built from wires, servers, and electromagnetic signals, then the quantum internet is built from something far stranger. It's built from entanglement. The idea sounds ambitious, almost impossible. A global network that uses quantum states instead of electrical pulses. A communication system where security isn't enforced by firewalls or passwords, but by the laws of physics themselves. And at its heart lies the same phenomenon that once kept Einstein awake at night. Two particles behaving as one, no matter the distance. Let's start with why we even need it. The internet we use today is powerful, but fragile. Data can be intercepted, copied, or tampered with. Encryption protects us, but encryption relies on math, and math can be broken. Quantum computers, once mature, will tear through classical encryption like tissue paper. The codes we use to protect banking, health records, even state secrets, all of it will be vulnerable. So what comes next? A system where security isn't just strong, it's unbreakable. That's what a quantum internet promises. How does it work? Instead of sending bits, zeros, and 1s, you send qubits, particles like photons prepared in quantum states. And instead of relying on passwords or long prime numbers, you rely on entanglement. Here's the trick. Suppose you and I share an entangled pair of photons. If I measure mine, and you measure yours, the results are correlated in a way that no one else can predict. If someone tries to intercept or measure them, the entanglement breaks, instantly revealing the intrusion. This principle underpins quantum key distribution, a way to generate secret cryptographic keys that only the intended parties can share. If anyone eavesdrops, the act of measurement itself leaves evidence. But a real quantum internet goes beyond keys. It uses teleportation of quantum states, just as we saw in the last chapter. Imagine nodes, quantum repeaters, scattered across the globe. Each node shares entangled pairs with its neighbors. When you want to send quantum information across the world, the state can be teleported from one node to the next, hopping across entangled links like stepping stones. The result? A web of entanglement. A network that spans continents, oceans, even space. This isn't just theory. In 2017, China launched the Micius satellite, named after an ancient Chinese philosopher. From orbit, it distributed entangled photons to ground stations thousands of kilometers apart. The experiment was historic. For the first time, scientists used space to create an entangled link between cities. In practice, this means you could sit in Beijing and establish a secure quantum key with someone in Vienna, guaranteed by entanglement, not by trust. The dream is to scale this up into a quantum backbone, satellites, fiber optic links, and ground stations forming the skeleton of a new kind of internet. One that isn't just faster or more powerful, but fundamentally more secure. And yet the implications go even deeper. Because in a sense, a quantum internet isn't just about communication. It's about rewriting what it means to be connected. In the classical internet, every message is a copy. When you send an email, a file, or a photo, you're duplicating information and transmitting it across cables. But in a quantum internet, no information is ever copied. It's transferred, reconstituted at the other end while the original is destroyed. No copies exist in between, no backups for an eavesdropper to steal. And this raises a startling possibility. If you can entangle distant nodes, entire labs, even entire cities, then the network itself begins to feel less like a chain of links and more like a single system. A shared quantum state stretched across the globe. Think about that. Not just an internet of devices, but an internet of entangled realities. The vision is still young. The technology is fragile. Photons get lost in fiber optics. Entanglement decays over distance. Quantum repeaters are still experimental. Building a global system will take decades of work. But the principle is proven. We can generate entanglement on demand, We can teleport quantum states. We can detect eavesdropping with absolute certainty. We can stretch connections across hundreds, even thousands of kilometers. The next step is scaling up, and when that happens, the world will change. Because the quantum internet isn't just another upgrade. It's a different category of communication, one that doesn't just move data. It reshapes our relationship with information itself. And it all begins with something Einstein once dismissed as impossible. Quantum cryptography, unbreakable codes written in physics. When most people hear the word cryptography, they think of secret codes, spy agencies, or hackers pounding on keyboards in dark rooms. But modern cryptography isn't about secret alphabets. It's about mathematics. Your online banking, your email, even the padlock icon in your browser, all of it relies on math. The keys that keep your data safe are made of enormous prime numbers, so large that cracking them would take classical computers millions of years. But here's the problem. Quantum computers won't need millions of years. They'll tear through classical encryption like a knife through paper. The codes that protect global finance, diplomacy, and personal privacy, they'll crumble. So physicists asked, what if the only way to make encryption truly secure is to stop relying on math altogether? What if security could come from physics? This is where quantum cryptography enters. At its heart lies a simple but devastatingly powerful fact. In the quantum world, you cannot observe something without disturbing it. Think about it. If you try to measure a particle's polarization or spin or position, you inevitably change it. There is no look but don't touch. No eavesdropping in secret. Observation leaves fingerprints. Now imagine using that principle as a shield. Suppose you and I want to share a secret key, just a random string of bits that we can use later to encrypt messages. Normally, we'd send this key across a network, hoping no one intercepts it. But with quantum cryptography, we don't have to hope. We can guarantee. Here's how. I prepare a stream of photons, each in one of 4 possible polarization states: horizontal, vertical, diagonal left, diagonal right. I send them to you one by one. You measure them, but you don't know which basis to use. Sometimes you'll choose correctly, sometimes incorrectly. Later, we compare notes over a classical channel, throwing away the mismatched measurements. The remaining ones form our shared secret key. Now, what happens if an eavesdropper tries to intercept? They can't just copy the photons. Remember, quantum states can't be cloned. If they measure, they disturb the states, introducing errors. And when we compare a sample of our data, we'll notice the discrepancy. Eavesdropping becomes detectable. Not because we outsmarted the spy, but because nature itself refuses to keep secrets from us. That's the brilliance of quantum cryptography. This protocol is called BB84, proposed in 1984 by Charles Bennett and Gilles Brassard. At the time, it seemed futuristic, maybe even impractical. But today, it's real. Quantum key distribution, QKD, has been demonstrated across cities, across countries, even across space. In 2017, China's Micius satellite distributed quantum keys between Beijing and Vienna, more than 7,000 kilometers apart. The link was secure not because of encryption math, but because of entanglement. It was the first international quantum encrypted video call in history. Unhackable, unbreakable, protected not by trust but by physics. And the technology keeps improving. Fiber optic networks have carried quantum keys over hundreds of kilometers. Researchers are building quantum repeaters to extend these distances further. The goal is clear: to weave QKD into the very fabric of the global internet. But the implications go beyond security. Because what quantum cryptography really shows us is that entanglement is a resource. It can be engineered, deployed, commercialized. It can protect governments, banks, and ordinary citizens. It transforms secrecy from a mathematical arms race into a fundamental guarantee. For the first time in history, we can create codes that aren't just difficult to break. They're impossible to break. Unless, of course, you're willing to break the laws of physics. Still, quantum cryptography has its limits. It doesn't make all information perfectly secure. It doesn't stop people from leaving their passwords on sticky notes or trusting the wrong server. Human error will always be the weakest link. But it does something profound. It closes the final backdoor. It ensures that, at least in principle, no one can secretly listen in without being caught. That's more than technology. That's a new kind of trust, one built into the structure of the universe. And once you can secure information this way, the next natural question is, what if we don't just send secrets with entanglement? What if we compute with it? Because entanglement isn't just good for keeping data safe. It's also the secret ingredient for something even more ambitious. Quantum computers, machines that don't just process information like classical computers do, but that use superposition and entanglement to unlock forms of computation we've never seen before. Quantum computers. Why entanglement is the ultimate resource. Imagine you're solving a maze. A classical computer is like a person walking down one path at a time. It checks, left, dead end. Backtrack. Right, dead end. Backtrack. Step by step, trial by trial, until it finds the exit. Now imagine instead of one person, you had thousands of ghostly versions of yourself, each trying a different path at the same time. And at the end, all the ghosts collapse into one answer, the correct route through the maze. That's the promise of a quantum computer. Not a faster calculator, not just more powerful hardware, but a fundamentally different way of processing information. And the key to this strange power? Entanglement. Here's why. In a classical computer, information is stored in bits. Each bit can be either 0 or 1. That's it. Billions of bits strung together run everything from your phone to supercomputers. In a quantum computer, information is stored in qubits. A qubit can be 0 or 1 or a superposition of both. It's like a coin spinning in the air. Heads, tails, and everything in between until it lands. Now, superposition is powerful, but it's not enough. If qubits were just independent coins, they'd collapse into random noise. You'd gain nothing. What makes quantum computing work is that qubits can be entangled. When qubits are entangled, their states are no longer independent. They're linked, so that operations on one affect the others, no matter how far apart they are in the machine. Instead of isolated pieces, they form a web of information. This entanglement allows quantum algorithms to explore an astronomical number of possibilities at once, but still produce coherent, useful results. It's the difference between chaos and computation. Take an example. Suppose you're trying to factor a huge number, a task that underpins much of classical encryption. For a normal computer, the number of steps grows so quickly it becomes impossible for large inputs. That's why your bank account is safe behind prime number keys. But with entanglement, a quantum computer can weave all possible factors into a single quantum state, test them simultaneously, and interfere the wrong answers away. The algorithm, proposed by mathematician Peter Shor in 1994, would crack RSA encryption in minutes on a powerful enough machine. That's why governments, companies, and scientists are racing to build these devices. Not because they want faster video games, but because the stakes are enormous. Whoever controls quantum computing controls cryptography, logistics, simulation, drug design, finance, even materials science. And behind it all is entanglement. Without entanglement, qubits are just fancy dice. With entanglement, they're a machine that bends probability itself to calculation. But here's the fascinating twist. Quantum computers don't always beat classical ones. They're not faster at everything. They're specialized. They excel at problems where entanglement and superposition can be harnessed, searching large spaces, simulating molecules, optimizing complex systems. And this makes them not a replacement for classical computers, but a partner, a new tool in the toolbox, one that does things our old tools simply can't. Already, small quantum processors exist. with dozens or hundreds of qubits. They're noisy, fragile, error-prone. Entanglement is delicate, and maintaining it across many qubits is the central engineering challenge of our time. But progress is rapid. Companies like IBM, Google, and startups across the globe are building bigger, cleaner, more reliable machines. In 2019, Google claimed quantum supremacy, a demonstration that their quantum processors solved a problem in minutes that would take classical supercomputers thousands of years. The problem itself was useless, but the demonstration was historic. It showed that entanglement can be engineered, that this isn't just theory, that we are standing on the threshold of a new era in computing. And yet the story doesn't end in labs or corporations, because entanglement isn't limited by walls. It can be stretched, carried, shared. In fact, it can be transmitted across space. And when you do that, when you send entangled photons not just across fibers and cities, but into orbit and back, you begin to glimpse the future of something even larger than quantum computing. A future where entanglement doesn't just power machines, it connects planets. Entanglement in space, China's Micius satellite and global tests. For almost a century, quantum entanglement lived in the realm of the small. Electrons in labs. Photons in short fibers. Tiny systems, fragile and delicate, shielded from heat and noise. The great debates of Einstein and Bohr unfolded around blackboards and equations, not rockets and satellites. But today, entanglement has gone orbital. It's no longer just a laboratory curiosity. It's being tested, stretched, and verified under the harshest conditions imaginable, the vacuum of space. The pioneer of this new frontier is a satellite launched by China in 2016 named Micius, after a 5th-century Chinese philosopher who believed that the universe was bound together by unseen connections. The name could not have been more perfect. Micius was built to do something no one had ever dared before: create pairs of entangled photons in orbit and send them down to ground stations thousands of kilometers apart. The goal? To test whether entanglement, this fragile, ghostly link, could survive across such vast distances. Because on Earth, there's always interference. Fiber optic cables absorb photons. Air scatters them. Detectors have limits. Even the most careful experiments struggle beyond a few hundred kilometers. But space offers something Earth cannot: emptiness. No air, no wires, just the void. A perfect arena to see whether spooky action at a distance still holds when the distance is measured in continents. The experiment worked. From Micius, pairs of photons were fired toward 2 ground stations separated by over 1,000 kilometers. Each photon traveled alone, through the emptiness of space and then the turbulence of the atmosphere, into detectors waiting far apart. And yet, when the results were compared, the photons were still entangled. Bell's inequality was violated again, not across a few meters in a lab, not across a city, but across a distance the size of a country. It was a triumph. Not only did it confirm quantum mechanics once more, it opened a door to something larger: the quantum Internet of Space, a network of satellites distributing entangled photons across the planet, providing secure communication and teleportation of quantum states on a global scale. But the experiments didn't stop there. In 2017, Micius was used to perform the world's first quantum-encrypted video call between Beijing and Vienna. The call was unhackable, not because of clever algorithms, but because of entanglement. Any attempt to intercept the photons would have been instantly detected. It was the first time quantum mechanics had reached directly into the fabric of everyday communication. Other experiments used Micius to teleport quantum states from the ground to orbit, proving that teleportation isn't just a trick for labs, but a tool that can reach the stars. Why does this matter? Because entanglement in space isn't just about satellites and security. It's a test of the universality of quantum mechanics. For decades, skeptics wondered, maybe quantum theory only works for the tiny, the delicate, the microscopic. Maybe entanglement breaks down when stretched across macroscopic distances, or when exposed to gravity, or when tested outside the protective bubble of Earth. Micius gave an answer. It doesn't break. Even across 1,000 kilometers through orbit, atmosphere, and ground, the correlations still hold. Entanglement doesn't care about scale. It doesn't care about space. It doesn't even seem to care about gravity. It just works. And that fact carries a deeper philosophical punch. Because if entanglement really is universal, then the universe itself might be woven together by this invisible thread. Galaxies may have been born entangled. Black holes may be connected by it. Space and time themselves may be stitched out of quantum correlations. What began as Einstein's spooky action is now a working principle of the cosmos. Other countries are racing to catch up. Europe, the US, Japan, all are launching or planning quantum communication satellites. Ground-based networks are extending entanglement across hundreds of kilometers of fiber optics. One by one, the building blocks of a planetary-scale quantum network are falling into place. And the more we scale up, the stranger the implications become. Because entanglement isn't only about technology. It's also about testing reality in places we've never been able to test it before. What happens if we send entangled particles near a black hole? What happens if one photon falls deeper into gravity's well than the other? What happens when we stretch entanglement across planets, across interplanetary space, across light years? These aren't science fiction questions anymore. They're engineering projects, hard, expensive, but possible. And with every new experiment, we're forced to confront the same fact. The universe doesn't separate cleanly into here and there. Space isn't the ultimate divider. Reality is entangled. For the first time, we've carried that realization into orbit. And it won't stop there. Because if entanglement can cross continents, if it can cross orbit, then maybe, just maybe, it can carry us toward a cosmic-scale understanding of connection. A web of information that already exists, waiting for us to see it. And just when you think you've grasped the scope of this idea, a new twist arrives. Because entanglement might not just belong to particles in labs or photons in satellites. It might already be inside you, in the beating of your heart, in the chemistry of your brain, in the way birds find their way across the sky, or how plants harvest light. Entanglement in biology? Birds, plants, and living quantum mysteries. We often think of quantum physics as distant from life. It's for the cold, the microscopic, the artificial vacuum chambers and superconductors, lasers and labs. Biology, on the other hand, is warm, wet, chaotic. Cells are messy. Evolution doesn't care about elegance. It cares about survival. So how could something as delicate as quantum entanglement, this bizarre, fragile connection between particles, possibly exist inside living things? How could it survive the heat, the noise, the chaos of biology? The answer may surprise you, because nature has been quietly experimenting with quantum mechanics for billions of years. And in some cases, it might have beaten us to it. Let's start with a mystery. How do birds know where they are? Migratory birds can travel thousands of kilometers with astonishing precision. They cross oceans and continents, returning to the same patch of forest year after year. Scientists long suspected they must be using Earth's magnetic field like a compass. But magnetic fields are incredibly weak. You can barely detect them with instruments. So how does a bird do it? With just its brain. The leading theory is that birds see the magnetic field through quantum entanglement. Here's how it might work. In a bird's eye, there's a protein called cryptochrome. When light hits it, it excites electrons inside the molecule, creating a pair of so-called radical electrons. Two electrons that are still entangled. Their spins, tiny quantum properties, remain linked. These electrons evolve differently depending on the surrounding magnetic field. So as the bird flies, the Earth's magnetic field subtly shifts how those entangled spins behave, which may affect chemical reactions in the eye, altering vision slightly, giving the bird a kind of magnetic sense. In other words, the bird's internal compass might be built from biological entanglement. It's still a hypothesis, a difficult one to test, but evidence is growing. Scientists have shown that cryptochrome molecules can maintain quantum coherence for surprisingly long times, even at body temperature. If confirmed, this would mean that birds are natural quantum navigators, their brains hosting fleeting delicate quantum states as part of everyday life. And birds aren't the only suspects. Let's look at plants. Photosynthesis, the process by which plants turn sunlight into energy, is one of the most efficient systems in nature. It converts light into usable chemical energy with almost no waste. For decades, scientists thought this was just due to smart molecular design. But then came the surprise. In 2007, researchers observed something strange in photosynthetic complexes. Energy didn't flow randomly through the molecules like a bouncing ball. Instead, it moved in a wave-like pattern, sampling multiple paths simultaneously, a behavior suggestive of quantum coherence. It was as if the energy excited by sunlight was exploring all the routes through the molecule at once and choosing the most efficient one. This is the same principle behind quantum computing, and it might be happening in leaves. Some theories go further. Perhaps short-lived entanglement helps coordinate the energy transfer. The idea is controversial, but the fact remains. Quantum behavior is showing up in biological places we never expected. And then there's you, your brain. It's the most complex structure we know of in the universe. A pulsing jungle of 86 billion neurons, each firing, connecting, rewiring, learning. And for years, scientists dismissed the idea that quantum mechanics could play any role here. Too warm, too noisy, too unstable. But some researchers have begun to ask, what if? What if consciousness, memory, or cognition emerge in part from quantum effects? The most well-known and most debated proposal is the Orco-R theory by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that microtubules, tiny structures inside neurons, might host quantum superpositions that contribute to thought. It's highly speculative. Many neuroscientists are skeptical, but the very fact that this is even on the table tells you something. The boundary between physics and biology is dissolving. We used to think of them as separate realms, the cold precision of atoms versus the mess of life. But nature doesn't draw that line. We do. And here's the deeper insight. If life can exploit entanglement, if birds can see with quantum compasses, if plants can channel sunlight using quantum coherence, then the universe isn't just compatible with life. It may be optimized for it. Quantum mechanics, for all its strangeness, might not be an obstacle to life, but part of its very foundation. And that means entanglement isn't just a technology. It's not just for satellites and circuits. It could be woven into the story of life itself. From birds migrating over oceans, to leaves catching the light of ancient suns, to neurons sparking in your head as you listen to this very sentence. Entanglement might be there, hiding in the chaos, whispering through the noise, guiding processes we barely understand. But now, let's take a leap even further. If entanglement can exist in labs, in satellites, in living things, what about the universe itself? Could galaxies be entangled? Could space and time emerge from it? Could everything, from your thoughts to the shape of the cosmos, be part of one giant quantum connection? We begin to leave biology behind and step into the deepest questions of the cosmos. Black holes and information. Does entanglement burn in the firewalls? You've heard the story before. A star dies, collapses under its own weight, and vanishes into a black hole, a region of space so dense, so curved, that not even light can escape. We think of black holes as erasers. Once something crosses the event horizon, the invisible boundary of no return, it's gone. Information, particles, memories, atoms, everything is swallowed. But this story has a problem. A deep, disturbing, unresolved problem. Because while gravity tells us that a black hole can erase anything, quantum mechanics disagrees, and at the center of this conflict is entanglement. Let's take it slow. In quantum mechanics, information is never truly destroyed. If you know the state of a system, you can always, in principle, rewind the tape and figure out how it got there. Even when particles are entangled, the total information remains intact. It's one of the most sacred rules of quantum theory. But if that's true, then what happens to information that falls into a black hole? Does it get erased forever? Or does it somehow survive? This is called the black hole information paradox, and it nearly broke physics. Stephen Hawking was one of the first to raise the alarm. In the 1970s, he discovered something shocking: black holes aren't entirely black. They slowly evaporate. Thanks to quantum fluctuations near the event horizon, pairs of particles can appear. One falls in, the other escapes. This escaping radiation is now called Hawking radiation. Here's the problem. Hawking radiation is completely random. It carries no imprint of what fell into the black hole. It doesn't remember whether the black hole swallowed a shoe or a supernova. As the black hole evaporates, the information seems to vanish. And that violates quantum mechanics. So which is wrong? Our understanding of gravity or our understanding of quantum theory? This paradox split the physics world in two. Some argued that the information must be preserved, somehow encoded in the Hawking radiation in ways we don't yet understand. Others said maybe information really can be destroyed, and we need to revise quantum theory itself. But in the early 2010s, a new twist emerged, and it came from entanglement. Imagine this: a black hole emits Hawking radiation. Pairs of particles where one escapes and the other falls in. These escaping particles are entangled with their partners inside the hole. So far, so good. But as the black hole evaporates more and more, the new radiation has to somehow entangle with the old radiation and with what's still inside the hole. Here's the catch: quantum entanglement can't do that. A particle can't be maximally entangled with two different systems at once. It's like trying to be married to two people, each of whom thinks they're your only spouse. This creates a contradiction. If you try to force it, something must break. And the thing that might break is space-time itself. This led to the firewall paradox. Some theorists proposed that the event horizon, the smooth boundary of a black hole, might actually be replaced by a searing wall of energy, a firewall that incinerates anything that tries to cross. This firewall would break the entanglement violently. No more smooth space. No more gentle descent into the void. Instead, a harsh discontinuity. Space-time ends, because quantum rules refuse to be broken. But if that's true, then something deeply cherished dies. The idea that falling into a black hole would feel normal, at least at first. Einstein's general relativity says you wouldn't even notice the moment you crossed the event horizon. You'd float, drift, fall freely. But if firewalls exist, that smooth ride ends in a quantum explosion. And yet, many physicists hate this idea. It violates the principle of equivalence, the foundation of general relativity. It suggests that spacetime is not continuous, but stitched together with sharp seams, where entanglement rules over geometry, so others looked for a way out. And again, the rescuer was entanglement. In the past decade, new research suggests that maybe spacetime itself is not fundamental. Maybe it's built, quite literally, out of entanglement. In this view, space is nothing but the pattern of quantum connections between particles. When you reduce entanglement, space begins to fall apart. When you increase it, space becomes smoother, richer, more connected. This leads to a shocking possibility. The inside of a black hole may not exist unless it's entangled. That's not just poetic. It means that the geometry behind the event horizon, the curvature, the location, the very existence of inside, depends on the preservation of entanglement between the black hole and its radiation. Destroy that connection, and there's no inside to fall into. What does that even mean? It means that reality may be informational before it is spatial. And entanglement, the mysterious link between particles, may be the scaffolding on which all of space-time is built. This isn't just an abstract idea anymore. It's supported by models from quantum gravity, holography, and black hole thermodynamics. We're beginning to see glimpses of a world where geometry emerges from information, not the other way around. The black hole paradox is still not fully resolved. There are camps, arguments. Experiments are hard. You can't exactly poke a black hole and ask it questions. But here's what everyone agrees on. Entanglement isn't just a weird feature of quantum particles anymore. It's now a serious candidate for the fabric of space itself. And black holes, the darkest, most extreme objects in the universe, may be our portal to understanding it. The next step in this strange journey leads us somewhere even more radical. What if the surface of a black hole is not just hiding information, but generating space itself? And what if that's true for everything, not just black holes? What if the entire universe is a kind of hologram, where what you think is three-dimensional space is actually coded on a distant surface? That's where we're going next. The holographic principle, reality as entanglement woven on a surface. Imagine holding a snow globe. Inside, there's a tiny winter town, houses, trees, swirling snow. Everything looks three-dimensional. But now, imagine discovering something strange. Imagine realizing that every part of this tiny world, every flake of snow, every light in a window, isn't really inside at all. It's encoded on the glass. That's the idea behind one of the most mind-bending proposals in modern physics, the holographic principle. It sounds impossible, like science fiction, but it's been taken seriously by the world's leading physicists, including string theorists, black hole researchers, and experts in quantum gravity. And at its core, it's about one thing: entanglement. Let's trace how we got here. In the 1970s, Jacob Bekenstein made a remarkable observation. The entropy of a black hole, the measure of how much information is hidden inside, is proportional not to its volume, but to the area of its surface. This was bizarre. Normally, if you want to know how much stuff is in a room, you'd measure its volume. But for black holes, it seemed the information was somehow stored on the event horizon, the 2D boundary. Stephen Hawking's calculations confirmed it. The entropy of a black hole grows with the area, not the bulk. That raised a stunning possibility. What if black holes are just a special case? What if all of space-time works this way? What if the entire 3D universe is a kind of hologram, a projection from a 2D surface where the true physics resides? This is not just a metaphor. In 1997, physicist Juan Maldacena made it concrete. Working in the context of string theory, he proposed something now called the ADS/CFT correspondence. It's a duality between two completely different kinds of theories. On one side, you have a theory of gravity in a five-dimensional curved space, anti-de Sitter space, or ADS. On the other side, you have a quantum field theory without gravity, living on the four-dimensional boundary of that space. The two theories are mathematically equivalent. Every particle, every interaction, every motion inside the 5D space has a counterpart in the 4D boundary theory. One describes gravity in spacetime, the other does not. Yet they describe the same reality. It's like watching a movie and realizing the entire 3D story is encoded in 2D light on the screen. This discovery sent shockwaves through theoretical physics because it suggested that space and gravity are emergent phenomena. And more, that entanglement is the glue. Here's how it works. In the boundary theory, the 2D surface, the degrees of freedom are entangled with each other in specific ways. And when you analyze that entanglement pattern, you can reconstruct the geometry of the bulk, the inside space. Regions that are highly entangled appear close together in space. Regions with less entanglement are farther apart. So space becomes not a background stage, but a map of entanglement. In fact, the very shape of spacetime can change if you change the entanglement. This leads to a radical picture. Spacetime isn't fundamental. It's woven from entanglement. The threads of this weave are the invisible quantum links between parts of a system. If you untangle them, space itself can rip, bend, or vanish. This idea is no longer just a theoretical curiosity. In recent years, physicists like Mark van Ramsdonk and others have shown that if you take two regions of a quantum system and reduce the entanglement between them, the corresponding regions of spacetime pull apart. If you remove entanglement entirely, the space connecting them disappears. Entanglement isn't just a weird quantum property anymore, it's architecture. It's like finding out that the walls, floors, and ceilings of your house aren't made of bricks, but of shared memories. That the space you live in is nothing but relationships. This brings us back to black holes. If the information about what's inside a black hole is encoded on the surface, and that surface obeys the same rules as other quantum systems, then black holes are not exceptions, they're windows. They show us how holography works. More importantly, they suggest that everything might be holographic. Even you. Let's go even further. There's a reason why the holographic principle feels so disturbing. It suggests that what you experience as three-dimensional reality may just be the end result of processing a 2D pattern of entangled information. It's not that the universe isn't real. It's that the real universe may be encoded differently than it appears. You're not living inside a literal hologram like in Blade Runner or The Matrix. You're living in a world where the information needed to describe everything about your experience might live on a boundary far away, a boundary you'll never see. It's not just physics, it's metaphysics. And it forces us to ask, what does it mean for something to be real? Is reality the experience you have, or the code that generates it? And who or what writes the code? The answers may still lie in entanglement, not just as a curiosity, but as a creative force. Because if space emerges from entanglement, what else does? Could time itself be a product of entanglement? Could the arrow of time, the feeling of before and after, arise not from some ticking cosmic clock, but from the shifting, growing, and breaking of entangled relationships? That's the mystery we'll face next. ER equals EPR wormholes as entangled pairs. Let's begin with a thought experiment. You're standing on Earth. Your friend is on the other side of the galaxy. You're each holding one particle from a perfectly entangled pair. You measure yours. Instantly, you know the state of theirs. That's quantum entanglement. Spooky action at a distance. Now imagine something different. A wormhole. A shortcut through space-time, a tunnel that connects two distant regions of the universe. In science fiction, it's a highway for spaceships. In general relativity, it's a mathematical solution, first explored by Einstein and his colleague Nathan Rosen. They called it an Einstein-Rosen bridge. But what if those two ideas are really the same? Entanglement and wormholes. What if a wormhole is entanglement made geometric? That's the bold claim of a modern conjecture known as ER equals EPR, or Einstein-Rosen equals Einstein-Podolsky-Rosen. Let's unpack it. In 1935, Einstein co-wrote two famous papers, one with Rosen, introducing the Einstein-Rosen bridge, a kind of wormhole. One with Podolsky and Rosen, the EPR paradox, questioning quantum entanglement. Both involve strange, non-local connections. Both felt incomplete. Neither seemed satisfying. Decades later, physicist Leonard Susskind and others began to suspect the similarity wasn't coincidence. And in 2013, Juan Maldacena and Susskind proposed the bold unifying idea, ER equals EPR. Einstein-Rosen bridges, ER, are the same thing as Einstein-Podolsky-Rosen entanglement, EPR. That is, every entangled pair of particles is connected by a microscopic wormhole. It's not the kind you can travel through. It may be non-traversable, but it's real, at least in some descriptions of quantum gravity. And here's what's radical. It means that entanglement doesn't just look like a connection across space. It is a geometric connection, a literal bridge in space-time. To see how this could work, imagine a black hole. Now imagine creating a second black hole in a lab and entangling it perfectly with the first. According to ER equals EPR, those two black holes are now connected via a wormhole. From the outside, they appear as two separate objects. But in the right coordinate system, deep inside the mathematics of general relativity, they share a tunnel, a structure that joins them across space-time. This wormhole isn't something you could step into. There's no portal, no sci-fi gateway, but it's a concrete piece of geometry, part of the fabric of the universe. It's as if entanglement isn't just invisible information. It's architecture. It's how the universe stitches itself together. Here's where it gets deeper. This idea doesn't just explain black holes. It suggests a way to build space-time. If two black holes can be connected via entanglement, then what about particles? Fields? Atoms, maybe the entire structure of the universe, its dimensions, its distances, its geometry, is the result of countless threads of entanglement, some forming tight loops, others stretching across the cosmos. Wormholes, then, are not exotic exceptions. They're part of the underlying reality. When two things are entangled, it's not just spooky correlation. It's the same as a bridge, a line of connection in a deeper kind of space. And when enough of those lines are woven together, space itself appears. Here's a beautiful consequence. In normal physics, if two things are far apart, they shouldn't affect each other quickly. That's locality. If you tap a drum in Tokyo, it shouldn't rattle a window in Paris instantly. But in quantum physics, entanglement violates that intuition. Two entangled particles can appear to influence each other instantly, no matter the distance. With ER equals EPR, this isn't magic, it's geometry. The particles aren't separated in some hidden dimension. They're adjacent in a deeper topology. The wormhole connects them not through ordinary space, but through a more fundamental fabric. So when one changes, the other doesn't respond. They're just two ends of the same object, like pulling on a looped string. It looks far apart in space, but close in structure. This might sound like wild speculation, but it turns out that in the context of the holographic principle, the idea we explored last chapter, these wormholes emerge naturally from entanglement patterns. In some models, you can literally grow a wormhole by increasing entanglement between two systems. You can shorten it by changing the amount of correlation. You can even watch it open and close based on the flow of quantum information. This has deep implications for black hole physics, especially the infamous black hole information paradox. If information falls into a black hole and the black hole evaporates, where does that information go? For decades, physicists argued over whether it's lost forever, violating the rules of quantum mechanics. ER equals EPR offers a clue. If the particles that escape the black hole, Hawking radiation, are entangled with what's inside, then maybe they're connected by tiny wormholes. Over time, those wormholes knit together a path for information to escape, restoring unitarity, preserving quantum law. In other words, entanglement saves information via geometry. But the most profound aspect of ER equals EPR might not be in its specifics. It's the shift in worldview. We've long thought of space and time as the fundamental stage. Entanglement was just a strange side effect of quantum mechanics. But this flips the script. Now, entanglement might be the real fabric. Space is just what entanglement looks like when woven together in the right pattern. And wormholes? They're not science fiction. They're the physical expression of relationships, of unity between what seems separate. So next time you hear about entangled particles, two photons created in a lab, two electrons in a distant star, don't picture invisible strings, picture tunnels. Tunnels not of rock and fire, but of information. Tunnels that twist through the unseen architecture of reality, connecting not just places but possibilities. And that opens a final, haunting question. If entanglement and wormholes are the same, then could the universe itself be one giant entangled structure? Could you, me, galaxies, black holes, and time itself all be part of a single, unimaginable geometry? In the next chapter, we'll explore that thought. We'll ask if the entire cosmos was born entangled. and what that might mean for everything we think is separate. Cosmic entanglement. Were galaxies linked at birth? Imagine this. You're looking at two galaxies, separated by billions of light years. They've never interacted. No signal could have passed between them, not in the age of the universe. And yet, in some subtle way, their properties seem correlated. Their spins, their orientations, their motions, their structures. Coincidence? Or something deeper? What if, long before stars ever formed, long before atoms cooled, long before the cosmic microwave background even flickered into existence, these galaxies were already connected? Welcome to the mind-bending world of cosmic entanglement. The idea that entanglement may not be a small-scale oddity, but a vast structural feature of the universe, something woven into the birth of everything. Let's trace it back to where it all begins, the Big Bang. In the earliest moments after the Big Bang, the universe was unimaginably small, hot, and dense, a quantum soup of energy, particles, and possibilities. There was no here and there because everything was everywhere, all at once. At that scale, the rules of quantum mechanics dominated, which means the entire universe began in a single quantum state, a wave function, not of one particle or one atom, but of everything. In this primordial state, particles weren't separate. They didn't have individual identities. Instead, they were entangled, correlated in ways that no classical system could explain. Now, as the universe expanded and cooled, these correlations got stretched across space. Particles that were once side by side were pushed light years apart, but their quantum links didn't break. Because entanglement doesn't care about distance. It doesn't degrade over time or fade with expansion. It just is. And that leads to a radical possibility. What we now see as distant galaxies may have originated from entangled regions of the early universe. They may still carry the invisible fingerprints of that shared origin, but how would we know? Can you actually measure cosmic entanglement? Surprisingly, physicists have started trying. There's a phenomenon called cosmic variance, the idea that some patterns in the universe are more likely than others, based on quantum fluctuations in the early moments. These fluctuations are what seeded all the structure we see today. Galaxies, clusters, filaments of matter across the cosmic web. And buried in those patterns are subtle statistical signatures, tiny correlations between different patches of the sky. Unexpected alignments. Anomalies in the cosmic microwave background. These might be leftovers of early quantum entanglement, whispers from a time before time. Some researchers have even proposed using quantum information theory tools like entanglement entropy to study cosmology, because if space-time itself is built from quantum connections, then the geometry of the universe should reflect the information content of its wave function. In other words, we might be able to measure how entangled the universe is, not just in labs, but in the stars. And then comes the philosophical twist. If regions of space that are now billions of light years apart were once entangled, then the universe isn't really a collection of parts. It's a single whole. Space isn't a container holding things. It's an emergent property of quantum relationships. This connects back to the ER equals EPR idea from the last chapter. If entanglement creates connections, wormholes, bridges, unseen threads, then maybe the structure of the cosmos, its shape and size and curvature, all come from a vast network of entangled relationships. Maybe every point in space is connected to every other, not by wires or tubes, but by information. The early universe, then, was not just hot and dense. It was maximally entangled, and as it expanded, it didn't lose that unity. It just spread it out, like stretching dough filled with chocolate chips. The chips are farther apart, but they came from the same batch. There's another angle to consider, the inflationary universe. Right after the Big Bang, the universe is believed to have undergone a burst of exponential expansion, known as inflation. This period smoothed out irregularities and set the stage for large-scale structure. But it also did something else. It amplified quantum fluctuations. Tiny random jitters in the quantum fields got blown up to cosmic scales. These fluctuations are what eventually became stars, galaxies, and the structure of the universe. And because these fluctuations were quantum in origin, they were entangled. So the very seeds of galaxies, the earliest imprints of everything we now observe, were quantum-linked. This isn't speculation. It's supported by the statistical patterns we see in the cosmic microwave background, the faint afterglow of the Big Bang, those ripples. They're not just random noise. They're the echo of entanglement, amplified by inflation, frozen into space, and visible to our telescopes. And here's where things get even stranger. If the early universe was a single quantum state, and that state contained all the information about every particle, every fluctuation, every possibility, then in some sense everything we observe is part of one grand entangled system. Not metaphorically, literally. The particles in your body may be entangled with particles in a galaxy you've never seen. The laws of physics may emerge from the pattern of these connections. And space itself might be nothing more than a graph of relationships, not a background stage. That's why some physicists believe entanglement is more fundamental than space-time. That without entanglement, space wouldn't exist. No here, no there, just chaos. But because the universe was born in a deeply entangled state, space unfolded as a byproduct. Time, too. And all the separations we now observe are just illusions, views from inside a system that was never truly divided. So the next time you look up at the night sky, imagine this. Every star you see, every galaxy, every glowing nebula is not isolated. It's linked, not by light or gravity, but by the memory of a shared quantum birth, a memory that never faded. Because in the deepest fabric of the cosmos, separation is an illusion, and entanglement is the truth. The multiverse angle, entanglement across possible worlds. What if every choice you didn't make, every path you didn't walk, every possibility that didn't happen, actually did happen, just not here? This isn't science fiction. It's one of the strangest, most controversial interpretations of quantum mechanics. And entanglement is right at its heart. Welcome to the many worlds interpretation of quantum physics. A reality where every quantum event causes the universe to split, where everything that could happen does happen, just in another branch of the multiverse. But here's the deeper question. If all these parallel realities exist, can they interact? Can entanglement reach across worlds? And if so, what does that mean for our universe? To answer that, let's start with a puzzle. You've probably heard the standard story of quantum measurement. A particle exists in a superposition, say spinning both clockwise and counterclockwise, until you observe it. And then, somehow, that uncertainty collapses. One possibility becomes real. The others vanish. That's the Copenhagen interpretation. And it's useful. But it's also deeply unsatisfying, because it never really explains how or why the collapse happens. It just says, don't ask. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a bolder approach. It says, there is no collapse. When you measure the particle, the universe splits. In one branch, you observe clockwise. In another, you observe counterclockwise. Both outcomes happen. Both are real. They just occur in different versions of you, in different branches of the universe. And this is where entanglement gets truly weird. In the many worlds view, entanglement doesn't link two distant particles across space. It links versions of reality across branches of the multiverse. Imagine two particles entangled. You measure one, say spin up or spin down. According to many worlds, you don't just get one result, you split. In one branch, you see spin up. In another, spin down. But, and here's the catch, your measurement also determines the outcome for the other particle. So in the spin-up branch, the second particle must be spin-down. In the spin-down branch, it must be spin-up. The correlation is preserved within each world. Entanglement, then, is the glue that keeps these parallel branches consistent. It ensures that even though you've split, the world around you stays coherent. This means entanglement isn't just across space, it's across possibility. Here's a wild thought. Every time an entangled system is measured, the universe branches. But those branches don't drift apart randomly. They mirror each other. The outcome of one determines the outcome of the other in every world. This is how quantum computers work. They don't just process one answer. They explore many possible answers at once, in many branches of reality, and then interfere those branches to extract the right result. Quantum algorithms depend on entanglement across possible paths. So in a very real sense, your quantum device is exploiting the structure of the multiverse to compute. You're not just calculating, you're navigating through worlds. But now let's go one level deeper. Could these branches, these other worlds, ever interact? That's usually where physicists draw the line. Many worlds assumes that after branching, the worlds become non-communicating. They evolve separately. They can't influence each other. But recent ideas in quantum cosmology and information theory have begun to push on that boundary. For example, the many interacting worlds hypothesis. It suggests that what we think of as quantum randomness is actually the result of tiny interactions between neighboring worlds. That the reason particles seem probabilistic is because they're being subtly nudged by the unseen presence of other realities. It's speculative, of course, but it offers a tantalizing possibility that the multiverse isn't made of isolated worlds, but of entangled ones. And entanglement isn't just a link between particles. It's the architecture of reality, the way worlds split, the way they stay coherent, the way they whisper to each other from across the quantum foam. Here's an analogy. Imagine the multiverse as a massive branching tree. Each branch is a possible reality. Each leaf is a version of you. Entanglement is the fiber of the tree, the pattern in the wood that keeps the branches connected, consistent, structured. It's what makes the tree a whole, not just a chaos of splinters. Without it, the universe would be random noise. With it, it's a living structure of meaning, pattern, and consequence. And maybe that's what reality is, not a single, solid world, but a shimmering superposition of worlds, entangled and interwoven. A place where every action echoes across possibility, where every measurement opens a door, where every pair of entangled particles is also a pair of entangled futures. If that's true, then maybe entanglement isn't spooky. Maybe it's the most natural thing in the universe, because it's how the universe remembers what it could have been, and what, somewhere, somewhen, it still is. Entropy, time, and entanglement. Why the arrow of time may be hidden inside it. You never wake up to find the coffee in your cup getting hotter. You never watch broken glass leap off the floor and reassemble itself. No matter how long you wait, the ashes of a fire won't form logs again. The universe moves one way, forward. We live with this arrow of time every moment of our lives. It gives our memories direction, our stories a beginning and end. It creates the difference between birth and death, cause and effect, past and future. But physics doesn't care. The equations that govern the universe work just as well in reverse. Drop a ball, the math works. Rewind the tape, watch it bounce back up into your hand. The same math still works. There's no preferred direction in the fundamental laws. They don't say, this way is forward. They're symmetrical, timeless, reversible. So the question becomes, if time has no direction in the laws of physics, why do we experience one? The usual answer is entropy. But in recent years, something deeper has begun to emerge. What if entropy is just a shadow, and what's casting that shadow is something quantum? What if the arrow of time is written, not in heat, but in entanglement? Let's begin at the start of the universe. Literally, the Big Bang wasn't just hot and dense, it was also extremely ordered. Low entropy, low chaos, a smooth, simple state. This is bizarre. You'd think the birth of the universe would be wild and messy, particles flying everywhere, chaos from the first instant. But instead we find a mystery. The early universe was pristine. Why? entropy by definition tends to increase. That's the second law of thermodynamics, and it's why we feel time moving forward, from low entropy order to high entropy disorder. But it only works if you start in a low entropy state. So we've pushed the question back. Not why does entropy increase, but why did it start so low? Here's where entanglement enters the picture. Because in quantum mechanics, entropy isn't just about messiness. It's about how much information you lose when you look at part of a system. And that's where entanglement entropy comes in. Imagine the universe like a library. Each book represents a particle. Each page, a possible state. If the books are perfectly isolated, reading one tells you nothing about the others. That's low entanglement. But if the books are linked, cross-referenced, mirrored, woven together, then reading one automatically tells you something about another. That's high entanglement. And here's the key insight. As the universe evolves, its subsystems, atoms, molecules, photons, fields, begin to interact. They don't just bounce off each other, they entangle. Their fates become intertwined. Their states become correlated in subtle, hidden ways. And the more they interact, the more entanglement entropy increases. From a detached perspective, you might say the system becomes messier. But from a quantum point of view, what's increasing isn't disorder, it's shared information. Entanglement isn't just noise. It's the deep structure of what the universe knows about itself. Now imagine rewinding time. To decrease entropy, you'd have to unentangle everything. Undo the connections. Break the correlations. Return every particle to its original independent state. But quantum mechanics doesn't let you do that easily. It's like trying to untangle a spider web by reversing the wind. You'd need to perfectly reverse every interaction, every photon, every nudge and twist that ever happened. You'd need a miracle. Which is why entropy almost never decreases. Because once entanglement starts, it grows. And the deeper it spreads, the more irreversible time feels. Here's where things get even stranger. Recent research suggests that entanglement might not just explain the arrow of time, it might explain time itself. In one experiment, physicists simulated a tiny quantum universe with only a handful of particles. When those particles were allowed to entangle, an arrow of time emerged. But when the particles were blocked from entangling, kept separate and pure, time stopped. There was no direction, no forward motion, just timeless oscillation. In other words, time appeared when entanglement appeared. It was not a background parameter. It was a consequence of how quantum systems became correlated. This idea leads to a radical possibility that the past and the future are defined not by what's real or unreal, but by how entangled things are. The past is the low entanglement state. The future is the high entanglement state. And time is the growth of those connections. Zoom out even further. In black hole physics, we've discovered that the surface area of the event horizon, not the volume, determines how much information is hidden inside. This insight has led to the holographic principle, the idea that the universe is like a 3D illusion, projected from 2D information stored on its boundaries. And what encodes that information? Entanglement. In fact, some physicists have proposed that space-time itself, its shape, its geometry, even its smoothness, arises from entanglement patterns in underlying quantum systems. Which means time is geometry. Geometry is entanglement. And entanglement is everything. Now, go back to that coffee cup. You think it's cooling down because heat is escaping into the air. But from another perspective, what's really happening is this. The molecules in the cup are becoming more entangled with the air around them. The correlations are spreading. Information is being shared. The world is weaving itself together, one moment at a time. And that's what you feel as the passage of time. So what is time, really? A ticking clock? A burning candle? A fourth dimension? Or is it something stranger? Something born from the quantum links between everything and everything else? A measure of how tightly the universe has braided itself together? And if that's true, then perhaps the most fundamental experience we have, the feeling of time itself, isn't a feature of the cosmos. It's a story written by entanglement. Beyond science, philosophy, and meaning. At this point in our journey, we've crossed the mathematical and experimental landscapes of quantum entanglement. We've seen particles affect one another across space. We've seen information teleport. We've watched reality bend, shift, and defy everything classical physics ever promised. But now we arrive at the most unsettling part of the journey. Because what started as a scientific question, how do particles behave when entangled, has opened something deeper, not just about atoms, but about us, about perception, about knowledge, about what it means to exist. This final act isn't about equipment or equations. It's about confronting the idea that our universe is not what it seems. That reality, the solid, dependable thing we think we live in, may not even exist until we look at it. And if that's true, what is reality? Imagine standing in a dark room with a flashlight. You shine the beam on a chair, and now the chair is real. But everything outside the beam? You can't see it. Is it there? Or is it waiting for you to look? This is not a metaphor. This is quantum mechanics. At the heart of quantum theory is a disturbing truth. Until you measure a particle, it doesn't have a definite state. It exists in a cloud of probabilities, a superposition of all possible realities, not a blurry picture of a real thing. But something deeper, it doesn't have properties until it's observed. You can't say the particle is here or there. You can't say it has spin up or spin down. You can't even say it exists as a particle at all. You only get a real answer after you ask the question. And when you do, something collapses. The wave function, that ghostly math cloud of possibilities, vanishes, and only one outcome remains. It's as if reality only congeals the moment it's witnessed. Now pause. This isn't just about atoms. It's about everything. If the smallest pieces of the universe aren't real until they're observed, and everything big is made of those small things, then what does that make your chair? Your room? Your memories? You? Let's go deeper. Consider this experiment. A single photon, a particle of light, is sent through a beam splitter. It could go left or right. Both paths are equally likely. Now, quantum mechanics says, until you check, the photon doesn't choose. It goes both ways. It travels left and right. It interferes with itself. It creates wave patterns, the same way ripples in a pond overlap and cancel. But here's the twist. If you place a detector on the left path to check whether the photon went that way, the interference pattern disappears. The photon chooses a path. And now, it's as if it never went both ways at all. But nothing touched the photon. No force altered it. Only your decision to observe it changed the outcome. This is known as the measurement problem, and it's still unsolved. How does a quantum system become a classical one? When exactly does a possibility become a fact? We don't know. What we do know is this: conscious observation seems to matter. And that's deeply unsettling. So what are the possible explanations? Some physicists argue the wave function is just a tool, a way of calculating outcomes, not something real. They say, of course particles aren't fuzzy. We just don't know where they are. But this view, called hidden variables, runs into trouble. Bell's theorem and its experimental confirmations show that no local hidden variable theory can reproduce quantum predictions. If reality exists independently of observation, it has to be non-local, that is, instantly connected across space. Others turn to the many worlds interpretation. In this view, the wave function never collapses. Instead, every possible outcome actually happens in a different universe. You measure the photon going left, there's another you measuring it going right, and another you where it gets absorbed or split or does something no one predicted. Reality doesn't collapse, it branches. The world is a tree of infinite outcomes, and you're just one leaf. But this raises new questions. If all outcomes exist, what determines your experience? What makes this version of you feel real? There are other interpretations too. The cubism approach says that quantum mechanics isn't about reality at all. It's about belief. It's a user's manual for updating your expectations when you make observations. Reality, in this view, is personal. Then there's the relational interpretation, which claims that there's no universal reality, only relations between systems. In other words, a particle's properties only exist relative to another observer. Reality isn't a book that everyone reads the same way. It's a conversation, and the meaning changes depending on who's listening. And yet, despite all these interpretations, the math never fails. We build quantum computers based on probabilities. We encrypt messages using quantum states that collapse when measured. We send photons into orbit and entangle them across continents. The theory works. But the picture it paints is surreal. A universe that doesn't exist until it's watched. A reality that depends on interaction. A cosmos made, not of stuff, but of questions and answers. So what is reality? A fixed, objective stage where particles dance? Or a quantum script, half-written, waiting for observation to fill in the blanks? Are we discovering the world, or participating in its creation? The more we measure, the more we learn. But the more we learn, the less solid the world becomes. It slips from substance into probabilities, from objects into correlations, from things into relations, and somewhere in that strange transition, between the unmeasured and the observed, between the question and the answer, is what we call real. Free will and determinism. Do we still have choice in an entangled universe? Imagine you're about to flip a coin. You hold it in your hand, you feel its weight, you prepare to toss. But before you do, pause. Ask yourself, did you choose to flip it? Or was the choice already written in your neurons, your childhood, the atoms of the universe? This question of free will has haunted philosophers for millennia. But quantum physics brings something new to the table. Because the universe it describes isn't clockwork and predictable. It's tangled, probabilistic, and strange. So here's the paradox. If the universe is random, how can you have meaningful choice? But if it's deterministic, how can you have any choice at all? To understand this, we need to go back, not to Newton, but to Laplace. In the 18th century, Pierre-Simon Laplace imagined a demon, a hypothetical intellect so vast, so precise, that it could know the position and velocity of every particle in the universe. To such a demon, the past and the future would be one. Every moment, from the birth of stars to the twitch of your finger, would be calculable, inevitable. In this world, free will is an illusion. You are a machine. Your thoughts, your choices, your love and guilt and curiosity, all just atoms bouncing, gears spinning, outcomes unfolding. This was the price of classical physics. A universe of certainty, and no room for freedom. Then came quantum mechanics. Suddenly, particles didn't have defined positions until measured. Outcomes weren't predetermined. They were probabilistic. You could calculate the chance that a particle would appear here or there, but not know for sure. Einstein hated this. God does not play dice, he said. But quantum experiments showed again and again, God plays dice. So does randomness restore free will? Not quite. If your decision is just the result of random quantum fluctuations, that's not you choosing. That's dice rolling in your brain. Freedom can't just mean not determined. It has to mean authorship, that you, in some meaningful sense, are the cause of your choice. So where does that leave us? Now, add entanglement to the picture. Two particles, once entangled, behave as a single system. Measure one, and the other responds, instantly, no matter the distance. Bell's theorem and the experiments that followed showed that these correlations cannot be explained by hidden variables set at the beginning. Somehow, the choice of what to measure here, now, affects what happens there, as if the universe isn't just non-local, but non-separable. This is where things get uncomfortable. Because to explain the correlations, you either have to accept faster-than-light influence, which violates relativity, accept many worlds, which splits reality endlessly, or accept that your choice of measurement wasn't really a choice at all. This last option, called superdeterminism, suggests that your decision to measure spin up instead of spin down was already baked into the fabric of the universe. Not just the outcome, but your decision to test it. In this view, everything is entangled. Not just particles, but choices, causes, even observers. The universe isn't just non-local in space, it's non-local in logic. This sounds extreme. It feels like a conspiracy, the universe rigging your thoughts in advance to match outcomes. But some physicists take it seriously, because it avoids the weirder parts of quantum theory. No spooky action, no many worlds, no collapse. Just absolute, total determinism, even of your mind. But there's a cost. If every thought is just part of a pre-written script, then the very idea of science, of experiment, of choice, of discovery, begins to dissolve. You weren't testing a theory. You were destined to find it true. Free will doesn't exist. And worse, neither does the idea of evidence. It's a closed loop. So what's the alternative? Some physicists and philosophers suggest a middle path. They argue that quantum mechanics introduces causal openness, that the future isn't fully determined, nor fully random. Instead, it's a landscape of possibilities, and conscious observers can influence which path becomes real, not by magic, but by participation. This is sometimes called participatory realism. It doesn't mean you can will particles into place, but it suggests that you are part of the unfolding, that reality is co-authored. In this view, free will isn't absolute control. It's the ability to steer within constraints, like sailing on a wind you didn't choose, but still choosing your direction. There's one more idea worth considering, and it comes not from physics, but from complex systems. Your brain is made of quantum particles, yes, but it's also made of emergent patterns, neurons, circuits, feedback loops. Just as water isn't just H2O, but waves and storms and currents, you are not just atoms, but mind. And minds might operate at a different level of reality, one that includes memory, intention, identity. In this layered universe, perhaps free will exists at the emergent level, not in the spin of particles, but in the patterns they form. You can't choose your neurons, but you can choose what story you tell. So, do we have free will in an entangled universe? We don't know. But we do know this: reality is not fixed in advance. Observation shapes outcomes. Entanglement connects distant parts of the universe in ways we don't fully understand. Maybe that means everything is determined. Maybe it means nothing is. Or maybe the act of asking the question is part of the answer. Spooky action or deeper order. In 1935, Albert Einstein sat down with Boris Podolsky and Nathan Rosen to publish what they believed would be the fatal blow to quantum mechanics. They weren't fringe skeptics. They were towering minds, frustrated by a theory that had somehow worked, but made no sense. What troubled them most wasn't the equations. It was what those equations implied. According to the quantum world, two particles that interacted could become entangled, a condition where their properties were no longer separate. Spin, momentum, position, these things became bound together. And here was the absurdity. Measure one particle and the other instantly responds, even if it's light years away. Einstein called this spooky action at a distance. He hated it because it seemed to violate the most sacred principle in physics: no influence travels faster than light. So he and his colleagues proposed something else, a hidden story beneath the surface. They imagined that particles carry hidden variables, secret instructions written at the beginning, like two identical letters mailed to opposite sides of the galaxy, already sealed and signed. When you open one and read it, you aren't changing the other. You're just seeing what was already decided. It's a comforting thought. It saves the principle of locality that causes don't leap across space. And it saves realism, the belief that particles have properties even when no one's looking. It would mean quantum mechanics is just incomplete. A statistical shortcut. covering up a deeper, more sensible order. This idea became known as the hidden variables theory. For decades, it remained a serious possibility, because nobody could prove, not just by math, but by experiment, that the universe wasn't hiding something. That is, until a quiet genius named John Bell came along. In the 1960s, Bell devised an idea so clever, it still feels like magic. He didn't try to find the hidden variables. Instead, he asked, if they existed, what limits would they place on correlations? He derived a mathematical inequality, now called Bell's inequality, which acts like a test. If you entangle two particles and measure them in various directions, any local hidden variable theory would have to obey certain statistical rules. But quantum mechanics predicted a different pattern, stronger correlations than any classical theory could explain. It was like a lie detector for reality itself. And when experiments were finally performed, decades later, they consistently broke Bell's limits. The universe, it seemed, didn't obey classical common sense. But maybe we're not being fair to hidden variables. Maybe we've misunderstood what they imply. One of the most ambitious proposals came from a physicist named David Bohm. His theory, Bohmian mechanics, takes the standard quantum wave function and adds something extra, particle positions that are always definite, guided by an invisible pilot wave. It's a strange picture. Particles don't just exist in a blurry cloud of probabilities, they follow real deterministic paths. But those paths are steered by a field that spans the entire universe. This field contains non-local information, meaning it can link particles across space. So Bohm's model keeps determinism but gives up locality. In other words, the universe still behaves like a machine, but a machine that's wired together in ways we can't see. This, too, has a cost, because if you accept Bohm's picture, you're forced to believe in a preferred frame of reference, a hidden structure of space-time that contradicts special relativity. It works mathematically, but it breaks something deeper, the idea that physics looks the same to all observers. So we face a choice: keep locality and give up realism, keep realism and give up locality, or give up both and admit we don't understand reality at all. There's a fourth option, of course, and it's far stranger. Instead of adding hidden parts to explain quantum weirdness, what if you just accept the weirdness? This is the stance of standard quantum mechanics. No hidden variables, no deeper story. Just the wave function and your measurement of it. In this view, the universe doesn't have definite properties until you ask. Reality is relational, not a set of fixed things, but a web of interactions. It's like a script with no actors until someone steps on stage. To many physicists, this is unbearable. It feels like abandoning truth itself. But to others, it's not a failure, it's a revelation. Maybe the problem isn't with quantum theory. Maybe it's with our expectations. Here's the uncomfortable truth. For hundreds of years, we've assumed the world is made of things. Objects with properties. Causes with effects. Events happening in time. But quantum entanglement doesn't care about our categories. It connects particles across space with no signal, no cause, no explanation. It doesn't tell us why. It just shows us what happens. And what happens, again and again, violates every classical instinct. So maybe the search for hidden variables is a relic of our need for comfort. A need to believe that behind the veil, the world is still reasonable. But what if reality is not hidden, just stranger than we can imagine? As we move forward, this tension remains unresolved. Bohm's theory is still studied. Superdeterminism has vocal defenders. New mathematical frameworks try to rescue locality, or realism, or both. But the experiments keep pointing in the same direction. Nature is non-local. The universe is not a collection of separate parts. It's a single, holistic system, connected in ways we're only beginning to grasp. Maybe someday we'll find a deeper theory. But for now, the best we can do is listen to what the particles are telling us, even when they whisper across the void. The spiritual temptation. Somewhere between the math of quantum physics and the silence of meditation retreats, a strange convergence has taken place. On one side, you have physicists working in labs, aligning photon beams, calculating spin correlations, testing statistical inequalities. On the other side, you have poets, mystics, and seekers, staring at the stars, breathing through mantras, trying to feel one with the cosmos. They seem like opposites. And yet, the concept of entanglement has drifted slowly, quietly, into the spiritual lexicon. How did this happen? How did a cold mathematical phenomenon become a metaphor for human connection, for cosmic unity, for oneness? To understand that, we need to step carefully through both the science and the temptation to make it say what we want. It starts with a feeling. If you've ever held someone's hand and felt like the world faded away, if you've ever stood beneath a night sky and felt like you were part of something vast and invisible, you already know the seed of the idea. Entanglement seems to confirm something people have intuited for centuries, that separation might be an illusion, that beneath the surface everything is connected. It's an old thought, but for the first time in history, science seemed to whisper it back. When two particles interact and become entangled, they stop behaving like individuals. They become part of a shared quantum system, no matter how far they drift. Measure one, and you instantly know something about the other. To the spiritual mind, this sounds like love, or empathy, or fate. But is it? The science says something more specific and more careful. Entanglement doesn't let information travel faster than light. It doesn't let you send thoughts across space or heal someone with your mind. What it does show is that quantum systems are not built from independent parts. They are described by a joint wave function, one that cannot be factored into pieces. This isn't metaphor, it's math. When you look at two entangled particles, you find that their combined description is simpler, more elegant than treating them separately. And that, in its own quiet way, is profound. It means that wholeness is not just a poetic idea. It's a structural fact of the universe. This is where the temptation begins. Because it's easy to leap from particles to people. To say, if quantum particles are connected across space, maybe we are too. And maybe that's not completely wrong. After all, we are made of particles, and our brains do run on quantum chemistry. But here's the problem. Entanglement is fragile. It breaks down with noise, with heat, with complexity. The kind of large, warm, chaotic system that is the human body is not a place where long-distance quantum entanglement survives. When people say they feel entangled with another person, it's a metaphor, a powerful one, but not the same as what's happening in a physics lab. Still, there's something beautiful here, even if we resist the exaggeration, because what entanglement really shows us is this. The universe doesn't split neatly into this and that. At the quantum level, interactions matter more than identities. What something is depends on what it's connected to. And if that's true for electrons and photons, maybe, just maybe, it points to something deeper about the nature of existence. Not that love is a quantum force, not that meditation can entangle your soul with the stars, but that the basic fabric of reality is relational, that nothing exists in perfect isolation, that meaning, identity, and behavior emerge from connection. And that idea echoes across science, philosophy, and spirituality. It's worth remembering that the word quantum has been used and abused in almost every mystical bestseller of the last few decades. Quantum healing, quantum manifestation, quantum consciousness. But most of those uses have no connection to actual quantum theory. They borrow the mystery, not the method. And yet, behind the noise, the real quantum mechanics is even more strange, and in many ways more beautiful than any spiritual repackaging. Because it forces us to confront something most people don't want to admit, that we don't understand the world, that our classical intuitions are built on sand, that reality at its core is not made of things, but of relationships. Einstein once wrote that the most beautiful thing we can experience is the mysterious. He also called entanglement spooky nonsense. Both quotes were true in their own way. And perhaps this is what entanglement teaches us above all, that mystery is not the enemy of science, it is its fuel. That wonder is not something you need to invent with metaphor. It's already there, in the equations, and that the greatest revelations often begin not with certainty, but with awe. In the next chapter, we'll wrestle with the ultimate question. If the world is this strange, if reality itself is probabilistic, relational, and incomplete, then what can we even know? What are the limits of human knowledge when the universe refuses to be pinned down? Let's go there. The limits of knowledge. There's a point in every journey where the path stops feeling familiar. At first, you're walking through forests of math and mountains of theory. But you still have a map. You know what's behind you, and you think you know where you're going. But then the landscape changes, and you realize something terrifying. You've gone beyond the edge of human intuition. Quantum entanglement was one of the first signs. But it was only the beginning. We like to believe that the world makes sense. That, with enough intelligence, we can model it, explain it, predict it. But the deeper we dig, the more we run into something unsettling. Our brains were not designed for this universe. Evolution didn't shape your mind to understand Hilbert spaces, non-local correlations, or probability amplitudes. It shaped you to throw rocks, recognize faces, and survive in a jungle of mid-sized objects, moving at mid-range speeds. You have no intuition for what a photon actually is. You can't feel a superposition. And no one, not even the top physicists, can truly imagine 4 entangled particles in a 16-dimensional probability space. So what do? We simulate. We visualize. We build metaphors. But at some point, the metaphors crack. The pictures fail. And we are left with equations that work, but don't feel real. This is where the limits of knowledge begin. It's not just that the universe is strange. It's that we may have hit a boundary in our ability to understand it. Think about this. We still don't fully know what a measurement is in quantum mechanics. We have equations that tell us how systems evolve, smoothly, predictably, until someone observes them. Then suddenly the system collapses into a definite state. But what is that collapse? When exactly does it happen? What counts as an observer? These aren't just philosophical games. They're questions we can't answer with any current theory. Even now, more than a century into quantum mechanics, we don't know whether the wave function is a real thing or just a tool for calculating probabilities. Is the universe fundamentally deterministic, and we just don't see the hidden variables? Or is randomness truly baked into the fabric of reality? These are not just unknowns. They might be unknowables. And the weirdness doesn't stop there. As we push experiments to their limits, trying to build bigger quantum computers, or test entanglement over cosmic distances, we're running into a new kind of problem. The tools we use are becoming as mysterious as the questions we're asking. We now rely on quantum simulations that are so complex, no human can verify them without a quantum computer. We write proofs that can only be checked by software. We explore ideas, like entanglement entropy or quantum gravity, that exist in spaces too abstract for any visual metaphor. In other words, our own creations are leaving us behind. And this raises a haunting possibility. We might be entering a future where we can build and test things that we will never truly understand. This isn't defeatist. It's the beginning of a new kind of humility. For most of scientific history, we assumed that knowledge meant control, that to understand something was to master it. But quantum entanglement reminds us, sometimes, knowledge means letting go of old intuitions. It means accepting that the universe doesn't care if its truths are uncomfortable or impossible to picture. And that might be the most mature form of knowledge there is. There's a beautiful story that physicist David Deutsch tells. He says the laws of physics are not just rules we discovered, they're deep explanations of how the universe works, and also how it limits us. Knowledge, in this sense, isn't a perfect mirror. It's more like a flashlight, illuminating small patches of reality while the rest remains dark. And sometimes, when we point that light toward the shadows, we realize just how little we can see, but we keep going. Because the act of asking, of wondering, is itself the spark that keeps us moving forward. So here we are. After decades of thought experiments, debates, equations, and lasers aimed at single atoms, entanglement has taught us not just about particles, but about ourselves. It has shown us the cracks in our reasoning, the blind spots in our minds, and the edge of the knowable. And yet, in that very limit, there's something beautiful. Because maybe the goal of science was never to fully explain the universe. Maybe it was always to expand our sense of what's possible. To show us that reality is more than what fits inside our heads. To remind us that awe is still allowed. And now, as we stand on the edge of everything entanglement has revealed, there's one last question to ask: what comes next? What is the future of entanglement? Not just in physics, but in philosophy, technology, and how we understand ourselves in a quantum world. Let's explore that in our final chapter. The future of entanglement. We began with a mystery: two particles born from the same event, drifting apart, and yet somehow still knowing what the other does. At first it sounded like superstition, then like bad philosophy, then like impossible physics. But here we are, at the end of a long and strange journey, and entanglement is no longer theory. It is no longer a ghost. It is no longer spooky. It is real. And now the question is, what will we do with it? The future of entanglement begins not in theory, but in engineering. Quantum computers, once the domain of science fiction, are now real. Small, unstable, noisy, but growing fast. At the heart of these machines is entanglement itself, used to create a kind of logic that isn't local, isn't classical, and isn't easily broken. A classical computer calculates. A quantum computer explores. It doesn't test each answer one by one. It entangles possibilities, allowing it to solve problems we can't even describe intuitively, factoring enormous numbers, simulating molecules for new drugs, optimizing problems that cripple current algorithms. Entanglement is what gives it power. But power is only part of the story. Look higher. The quantum internet is coming, a network not of signals but of entangled pairs. A web where information isn't sent but shared across distance, in ways that defy copying or interception. You'll hear the word unhackable. It's true. But it misses the deeper point. This isn't just security. It's a new architecture of connection, where trust is written into the physics and communication itself becomes quantum. China's Micius satellite has already tested it, entangling photons from space to the ground. Europe and the US are building their own networks: quantum repeaters, entanglement swapping, teleportation relays. These are becoming real systems, not just chalkboard diagrams. Within decades, the internet may run not on cables and code, but on entanglement. And it doesn't stop with computers and networks. Some scientists believe that entanglement may be the fabric of space-time itself, that the very geometry of reality, the distance between things, is nothing more than the pattern of entanglements between quantum fields. In this view, space is not fundamental. It emerges from connection. Wormholes might be entangled particles. Black holes might be quantum error-correcting codes. The universe might be a quantum computer. And that's not science fiction anymore. These are frontiers we are actively exploring, using mathematics so strange it feels like poetry, using experiments that bounce light off satellites, using concepts that take everything we thought we knew and quietly replace it with something deeper. But the most profound future of entanglement might not be in machines or space or physics. It might be philosophical. Because entanglement is a challenge to our deepest assumptions, that things are separate, that what's far is disconnected, that the world is made of pieces. Entanglement says no reality is relational. Particles don't just exist, they coexist. Outcomes don't just happen, they happen together. Information isn't owned, it's shared by design. And maybe, just maybe, that's not just a physics idea. Maybe it's a way of seeing ourselves. There is something quietly spiritual in all this. Not because we can hijack quantum physics to validate old beliefs, but because entanglement teaches humility. It teaches us that the world is stranger than control. That connection can be deeper than cause. That truth might not live in objects, but in the relationships between them. And as our civilization moves forward, building quantum systems, exploring the universe, extending consciousness into code and matter, we may need that humility more than ever. This is not the end of the story. It is the beginning of a quantum civilization, one that understands the universe not as a machine, but as a web of relationships, uncertainty, and subtle influence. A civilization that no longer needs certainty to move forward. That learns to build with probability, to design with superposition, to live with entanglement. Because if the deepest fabric of reality is made of relationships, then perhaps our future, our technology, our science, our ethics, must be too. So when you next look at the sky, at the stars billions of light years away, ask yourself something. What if you are still connected to all of it? Not metaphorically, not poetically, but literally, physically, entangled across time and space. Because the universe has always been strange. You're just starting to realize how strange. And it's only going to get stranger. Thank you for exploring the quantum unknown with us. This is the Midnight Particle, where the universe unfolds, one mystery at a time. If you want to keep diving deeper, stay curious, stay connected, and we'll see you in the next story.